but to our closest galactic neighbor, the Andromeda Galaxy, also known as M31. What mysteries of this colossal spiral could reshape our cosmic destiny, unlocking secrets about the universe's past and charting the course of its astonishing future? Prepare to explore an object so vast, so enigmatic, that its very existence challenges our deepest assumptions about reality. As we journey into the heart of galactic mysteries, don't forget to like and subscribe to explore these galactic mysteries with us, as every discovery within this cosmic titan brings us closer to understanding our own place in the vast, unfolding drama of the cosmos. Greetings, cosmic adventurers and stargazers. Today, we're setting our sights on a subject that has fascinated humanity for centuries, M31, the magnificent Andromeda Galaxy. Visible to the naked eye, even from light-polluted skies, this incredible barred spiral galaxy sits a mere 2.5 million light-years away, making it our nearest major galactic companion. But despite its proximity and prominence, Andromeda remains shrouded in profound scientific riddles. This video isn't just about what we know, it's about the thrilling, dramatic frontiers of what we don't know. We'll delve into its uncertain mass, the inevitable titanic collision with our own Milky Way, the perplexing processes of its star birth, the elusive influence of dark matter, and even the tantalizing possibility of exoplanets teeming with life. This exploration promises to be an adventure into the unknown, brimming with paradigm-shifting implications for our understanding of the universe itself. Whether you're a citizen astronomy enthusiast or just beginning your journey into the cosmos, prepare to be captivated by the unsolved riddles of this galactic enigma. Welcome to the grand cosmic stage, where M31 takes center stage as a celestial spectacle. Imagine standing on a distant world, gazing up at a sky dominated by a truly immense spire, its arms unfurling above the heavens. That's the Andromeda Galaxy, a breathtaking barred spiral galaxy, a cosmic island home to perhaps a trillion stars, dwarfing our own Milky Way in single stellar population. Yet for all its visiting glory, M31 remains an object of intense scientific scrutiny. Cosmic resonance, whose most fundamental properties continue to elude precise recognition. One of the most immediate and perplexing questions scientists grapple with concerns its sheer mass. For decades, astronomers have attempted to pin down its sheer mass. Initial estimates placed it as significantly more than perhaps twice as heavy. This perception painted Andromeda as the undisputed cosmic heavyweight of our local group of galaxies. However, more recent studies have thrown this long-held belief into disarray. Some observations suggest that M31 might actually be comparable in mass to the Milky Way, or even slightly less massive. This isn't just an academic debate. The true mass of this galactic titan has profound implications. It dictates the gravitational dance between M31 and our galaxy, influencing their trajectories and the eventual colossal merger that awaits us both. A more massive Andromeda would exert a stronger gravitational pull, accelerating our cosmic rendezvous. A less massive one might alter the very nature of the collision, perhaps leading to a gentler, more drawn-out embrace.
The techniques used to estimate galactic mass are incredibly complex. They involve observing the motions of stars and gas within the galaxy, as well as the velocity of its satellite galaxies. These observations, combined with gravitational models, allow scientists to infer the total mass, including the invisible, enigmatic component we call dark matter. But these measurements are fraught with uncertainties. Distances are hard to pinpoint precisely, and the three-dimensional motions of celestial objects are notoriously difficult to untangle. What hidden factors might be skewing our calculations? Could there be unknown gravitational influences at play? The adventure of unraveling M31's true mass is a testament to humanity's relentless curiosity, a dramatic quest that constantly pushes the boundaries of our observational capabilities and theoretical understanding. Consider the sheer scale of the challenge. We're not weighing a pebble. We're attempting to measure an object spanning hundreds of thousands of light years, composed of countless stars, vast clouds of gas and dust, and an overwhelming amount of unseen dark matter. Every photon we collect from M31 has traveled for 2.5 million years to reach us, carrying with it echoes of the past, but also uncertainties that complicate our current measurements. The ongoing debate about M31's mass is a perfect illustration of how science progresses, not in neat linear steps, but through a dynamic process of observation, hypothesis, and constant refinement. It's a reminder that even for our closest galactic neighbor, the universe still holds profound secrets. This uncertainty underscores the thrilling. If the question of M31's mass is a riddle, then its future encounter with the Milky Way is a cosmic drama of unparalleled proportions. Imagine two titanic spiral galaxies, each a sprawling city of stars, hurtling towards each other at incredible speeds. This isn't science fiction, it's the inevitable fate of our galactic neighborhood. Observations confirm that the Andromeda galaxy is approaching our Milky Way at approximately 110 kilometers per second. While that might sound fast, at a distance of 2.5 million light years, it means our collision is still about 4.5 billion years away. Yet this collision, dubbed Milkomeda or Milkdromeda by some astronomers, is perhaps the most significant cosmic event on our galaxy's distant horizon. But what exactly will this collision entail? Will stars violently smash into each other? Will our solar system be flung into the cold, dark void of intergalactic space? The good news for any potential future inhabitants of Earth is that direct stellar collisions are highly improbable. Galaxies, despite their immense star counts, are mostly empty space. The average distance between stars is so vast that even during a galactic merger, the likelihood of two individual stars colliding is incredibly small. Think of it like two swarms of bees flying through each other. Individual bees might pass very close, but rarely will they directly impact. Instead, the gravitational forces will be the primary sculptors of this cosmic dance. As M31 and the Milky Way draw closer, their immense gravitational fields will begin to distort and pull at each other, creating dramatic tidal forces. Spiral arms will unravel, new ones might form, and vast streams of stars and gas will be ejected into intergalactic space. The initial flyby might be the most dramatic, as the galaxies pass through each other, stretching and deforming. Then they'll swing back for repeated passes, gradually losing kinetic energy through gravitational friction, until they finally merge into a single, much larger elliptical galaxy. This new supergalaxy will likely be a chaotic, vibrant entity, a testament to the transformative power of gravity.
The long-term implications are staggering. Our familiar night sky, with its recognizable constellations, will be utterly transformed. Over billions of years, new stars will likely form from the compressed gas clouds triggered by the merger, leading to a burst of starbirth. The supermassive black holes at the centers of both M31 and the Milky Way are also destined to meet. As they spiral inwards, they will likely generate immense gravitational waves and possibly powerful X-ray flares, before eventually merging into an even more colossal supermassive black hole. This cosmic ballet is not merely an interesting theoretical exercise. It offers profound insights into galaxy evolution, providing a real-world example of the processes that have shaped the universe since the Big Bang. The ongoing study of this impending collision uses sophisticated computer
visible to the
simulations,
naked eye,
like those
and
performed
studied
by
by
teams
Persian
at
astronomers
NASA and
around
ESA,
900 AD.
which model the
The
gravitational
Andromeda
interactions
Nebula
and
was
predict the
thought to be a
various
part of the
outcomes.
Milky Way.
These simulations reveal the
In
intricate
fact,
dance
it was
of
thought that
matter
all
and
the stars
energy,
in the universe were
showcasing the
in our
dramatic
Milky Way
power
galaxy.
of gravity on a galactic scale. The exact
That
timeline
changed
and the
in
final
the early
configuration of the
1900s.
merged galaxy are still subjects of
In
intense
1923,
research and
Edwin
debate.
Hubble
highlighting
Cepheid
another one of
variable
the Andromeda
in the nebula.
galaxy's most profound,
The
unresolved
star
riddles.
altered the
Consider
course
the
of modern
immense
astronomy.
diversity of stellar populations.
The star goes by the
within
name
this
V1.
majestic spiral. Hubble Space Telescope images, like the panoramic view captured by the Panchromatic Hubble Andromeda
Here's
Treasury
Edwin
Survey,
Hubble's image of
have
Andromeda,
resolved individual
which was made on a
stars
4x5-inch
across
glass
vast
plate
regions of M31,
and dated
revealing
October 6,
populations of blue,
1923.
hot, young stars alongside
He originally
older,
identified 3
cooler,
stars
redder stars.
and marked each of them with an
This
N
incredible
for
data
nova,
allows
a
astronomers
class of
to
exploding
map
star.
out the star formation
Later,
history of
Hubble
the galaxy
realized
with
that the nova at the
unprecedented
top right
detail.
was actually
Yet
a
even with
Cepheid
this
variable.
wealth of information, the
He
why
crossed out the
behind
N
the patterns
and
remains
wrote
elusive.
var.
Why did
for
certain
variable.
regions burst with
He added
starbirth
an
in the
exclamation
past,
point
only to quiet
because he
down,
knew
while
that
others
this variable
continue
would
to
allow him
blaze
to
with new
calculate the
stellar
distance.
nurseries? The drama
You may
unfolds
recall
as
from our
astronomers
segment on
continue
distant
to probe
stars
these
that
discrepancies.
we covered how Harriet
By
Leavitt
studying the
discovered the
chemical
relationship
composition of
between
stars in
Cepheid
different
variable
regions,
frequency
they can infer the
and their
history of
intrinsic
gas
luminosity.
enrichment and star formation.
And once we know the
Analyzing
intrinsic
the
luminosity of
distribution
a
of
star,
dust, which
we
is
can use the
crucial for
apparent
shielding
luminosity
collapsing
and the
gas
inverse
clouds,
square law
offers further
to
clues.
determine how far away the
Each
star is.
observation brings us closer
And indeed,
to painting a
once the
complete
period was
picture.
measured,
But
at
the canvas
31.4
of
days,
M31 star
he
formation
knew
story is
he
still
had
far from
another
finished,
galaxy.
presenting a complex interplay of galactic dynamics, gas properties, and astrophysical
V1,
processes.
Distances
What
to
cosmic
stars
forces
were measured in
truly
thousands of
dictate
light years.
where and when new
After
suns
V1,
ignite in this
The
neighboring
universe
giant?
became a much bigger place.
M31 isn't just any
V1
spiral galaxy.
was over 2.5
It's classified as a
million
barred spiral
light
galaxy,
years away.
much like our own Milky Way. This designation refers to the prominent, elongated bar-shaped structure of stars and gas that extends from the galactic center. While the presence of a bar
Andromeda
is
is
a
a
common
beautiful
feature in many
barred
spirals,
spiral
its
galaxy
precise role
with
in
2
driving or
spiral arms
suppressing
that
star
glow
formation
with a massive
across
number
the
of new
Andromeda
stars.
galaxy is another fascinating
very
yet
much like our Milky
unresolved
Way.
scientific mystery. How does this central bar influence
But
the
Andromeda's
flow of
disk
gas and
is
dust,
220,000
and
light
consequently,
years
the birth
wide.
of new stars within its
That's more than
colossal
twice
reach?
the width
The
of the Milky
prevailing
Way.
theory is that galactic bars
But recent
act as
studies
cosmic
of star
conveyor
escape
belts.
velocities
They efficiently
indicate
channel
that both
gas
galaxies
from the
have
outer
the mass
regions
of
of the
about
galaxy
800
inwards
billion suns,
towards the central
counting
supermassive
stars,
black hole
gas,
and the inner
dust,
disk.
and
This
dark
inflow
matter.
of gas can lead to intense bursts of star formation in the central regions as the gas compresses and collapses under gravity. However, in the case of M31, observations suggest a more nuanced picture. While there is certainly
Light
a
from this
central
magnificent
bulge, which
galaxy
is very dense
left
with
its
older
stars
the rate
just over
of current
2.5
star
million
formation
years
in
ago.
M31's inner bar region isn't
When
as
the light that
dramatically
entered Hubble's
high as
telescope
one might expect
left
from such an
Andromeda,
efficient gas channeling
there were no
mechanism.
humans on Earth.
This contradiction poses
While
a
the light
significant
traveled
challenge
towards
to our
Earth,
general understanding
we came into
of how
being.
bars function
We
in
created and
galactic
lost
evolution.
great civilizations,
Could it be that
and we built the
M31's
telescope
bar is
that
relatively
caught the
young,
light
or
when it
perhaps
finally
its gas
reached our
tunneling
planet.
efficiency is somehow diminished compared to other barred spirals? Or are there other processes at play, such as powerful feedback from the central supermassive black hole, or even stellar winds from existing stars that are preventing the gas from efficiently forming new stars in the inner regions? The debate hinges on understanding the intricate dynamics of gas flow. When gas is channeled inwards, it can become turbulent and highly compressed.
In
conditions
2015,
ripe
the
for
Hubble
starburst.
Space Telescope
But if the
captured the
gas becomes
sharpest
too
and
hot
most
or too
detailed image
diffuse
ever
before
taken
it can
of the
collapse,
galaxy.
star formation
It shows
might
over
be suppressed.
100 million
The
stars
Andromeda galaxy,
and
with
thousands
its
of
sweeping
star
spiral
clusters
arms and vast
embedded in
stellar
a section of the
populations,
galaxy's
presents
disk,
a fascinating
stretching
laboratory
across
for studying
over
star formation.
48,000 light
Yet
years.
even here, a profound
It
mystery
traces the galaxy
persists.
from its central
How do
bulge
stars
on the left,
truly ignite across
where
such
stars
a
are
colossal
densely packed
structure?
together,
And what unique
across lanes
characteristics
of stars and
define
dust,
stellar nurseries
to the
in our
sparser
closest
outskirts
major galactic neighbor?
of its outer disk.
While we
on the right.
understand the basic principles of starburst,
Zooming into the
the
boxed
gravitational
field,
collapse of
we
dense
see some
gas and
foreground
dust
Milky Way
clouds,
stars
the
in the
specific
line of
rates,
sight to Andromeda,
distributions, and triggers of this
and a couple
process
of distant
within
spiral
M31
galaxies
offer
shining through
perplexing
Andromeda's
puzzles.
disk.
Unlike our own Milky Way, which shows more consistent rates of star
A large
formation
number of
across
star
its
clusters
disk,
can be seen
Andromeda
in this
displays
analysis
a
of
peculiar
Andromeda.
pattern. Observations reveal
A
regions
large
of
group of
intense,
blue stars in
active
the
star
galaxy
formation,
indicate
often
star-forming
located in
regions
the galaxy's
in the
outer
spiral
spiral
arms,
arms or in its
while the
ring-like
dark
structures,
silhouettes of obscured
particularly
regions
the 10
trace out
kiloparsec
complex
ring.
dust structures.
These areas blaze with the telltale signs
Underlying
of young,
the entire
hot,
galaxy
massive
is a
stars,
smooth distribution
bright
of cooler
H2
red stars
regions, where
that
hydrogen
trace
gas is
Andromeda's
ionized
evolution
by
over
fierce
billions of
ultraviolet
years.
radiation, glowing brilliantly. Yet other vast swaths of the galaxy appear surprisingly quiescent, with little evidence of new starbirth. Why this uneven distribution? What environmental factors,
Careful analysis
like gas
of Andromeda's
density,
proper and
stellar
radial
feedback,
motion
or even the
indicates that it
passage
is
of spiral
on a collision
density
course
waves,
with our
are
Milky
driving
Way.
or suppressing star formation in different parts of this grand
We'll
spiral.
conclude our coverage of Andromeda
One leading theory
with a look at its
suggests
closing
that the
velocity.
spiral arm structure itself plays a crucial
It's
role.
closing at
Spiral arms
14.4
are not
million
rigid
kilometers
structures,
per day.
but rather regions of
That's
enhanced
almost
density,
9 million
like
miles
traffic
per
jams on a
day.
cosmic highway.
But given
As
the
gas and
2.5
dust
million light
clouds
years between
encounter
us,
these density waves,
it
they are
won't get here
compressed,
for around
potentially
4
triggering
to
gravitational
4.5
collapse
billion years.
and subsequent star formation.
We cover this in
However,
depth
the precise
in a subsequent
mechanisms by
segment
which these
on
density
colliding
waves
galaxies.
translate into stellar nurseries are still debated. Are there specific velocities or compression thresholds required? How do magnetic fields within these arms influence the process? The inner regions of M31 in particular seem to be undergoing relatively little star formation compared to their gas content, suggesting that something is inhibiting the process near the galactic core. Could the powerful gravitational influence of M31's central supermassive black hole be a factor? Or perhaps the sheer density of existing stars and the resulting tidal forces?
Furthermore, the very formation and evolution of the bar itself are complex puzzles. How did this bar form in M31? Was it a result of internal gravitational instabilities within the disk, or perhaps triggered by past interactions with its satellite galaxies, such as M32 or NGC 205? The timescale over which a bar forms and stabilizes can dramatically impact its influence on gas dynamics and star formation. A more mature, stable bar might have different effects than a newly formed, evolving one. The history of M31's bar is inextricably linked to its overall star formation history, and deciphering this relationship is critical to understanding the galaxy's past and present.
Astronomers use advanced simulations to model the behavior of gas and stars within barred spirals, attempting to reproduce the observed star formation patterns in M31. These simulations allow scientists to test different hypotheses about bar formation, gas dynamics, and feedback mechanisms. Yet, the subtle interplay of these forces means that no single model perfectly explains M31's specific characteristics. This ongoing quest to unravel the bar's influence is a testament to the intricate ballet of cosmic forces at play, revealing how even a seemingly straightforward galactic feature can hold profound secrets about star birth and galactic evolution.
The history of the Andromeda Galaxy isn't just written in its grand spiral arms and vast stellar populations, it's also etched in the fleeting brilliance of its novae. These transient stellar explosions, while less powerful than supernovae, are crucial indicators of past stellar activity and hold valuable clues about the composition and evolution of M31. The story of novae in Andromeda stretches back over a century, offering a dramatic narrative of astronomical discovery and persistent scientific riddles. One of the most pivotal moments in the study of Andromeda's novae came in 1917 when Heber D. Curtis observed a new star flare up in the outer regions of M31. He called it S Andromedae. At the time, the true nature of spiral nebulae was hotly debated. Were they island universes, galaxies entirely separate from our Milky Way, or merely gas clouds within our own galaxy? Curtis's observation of S Andromedae, which appeared to be a nova but was significantly fainter than any known nova within the Milky Way, led him to conclude it must be incredibly distant, far beyond the confines of our galaxy. This observation, among others, provided crucial early evidence supporting the island universe hypothesis, directly contributing to what became known as the Great Debate of 1920 between Curtis and Harlow Shapley. Curtis's excitement over S Andromedae was palpable, as it hinted at the immense scale of the cosmos. He understood that if S Andromedae was truly a nova, its apparent faintness implied an extraordinary distance. This realization was a dramatic shift in astronomical thought, opening up a universe far vaster than previously imagined. The careful measurement of novae, particularly their peak brightness, which can be relatively consistent for certain types, allows astronomers to estimate distances to their host galaxies, serving as standard candles. This technique was later famously used by Edwin Hubble with Cepheid variables in M31, definitively proving its extragalactic nature.
Even today, novae and Andromeda continue to be studied intensely. Modern telescopes and automated surveys regularly detect these stellar outbursts, providing a continuous stream of data. Each nova offers a snapshot into the conditions within M31, revealing the presence of white dwarf stars in binary systems that are siphoning material from a companion. The frequency and distribution of these novae can tell us about the age and composition of stellar populations in different parts of the galaxy. For instance, a higher rate of novae might indicate a larger population of older, low-mass stars that have evolved into white dwarfs, providing insight into the galaxy's long-term stellar evolution. The specific types of novae observed, classical novae, recurrent novae, or dwarf novae, each carry unique signatures that can inform us about the binary systems producing them. Why do certain regions of M31 show more novae than others? Are there particular environmental factors, such as higher stellar densities or specific metallicity distributions, that promote the formation of these nova-producing binary systems? The ongoing study of Andromeda's novae, from Curtis's groundbreaking observations to today's automated sky surveys, represents a continuous journey into the heart of galactic evolution, offering a dramatic record of stellar life and death within this neighboring cosmic titan.
No discussion of the Andromeda Galaxy would be complete without acknowledging the transformative power of the Hubble Space Telescope. Its unparalleled vision has allowed humanity to resolve individual stars within M31 with breathtaking clarity, revealing a stellar tapestry of immense complexity and beauty. This feat of cosmic observation has not only confirmed the galaxy's independent nature, but has also unlocked a trove of data, enabling astronomers to probe its stellar populations in unprecedented detail. What secrets has Hubble's unwavering gaze unveiled, and what new riddles has it presented about the cosmic titan next door? In 2015, the ESA Hubble team released an astonishing image, the largest and sharpest image ever taken of the Andromeda Galaxy's outer disk. This single image, a mosaic of many Hubble exposures, resolved over 100 million individual stars across a 40,000 light-year-long swath of the galaxy. Imagine the sheer scale of that achievement, identifying and characterizing individual suns in a galaxy 2.5 million light-years away. This panoramic view, part of the panchromatic Hubble Andromeda Treasury Program, provided an unparalleled data set for understanding the galaxy's stellar content and its star formation history.
Before Hubble, images of Andromeda, even from large ground-based telescopes, typically showed it as a hazy patch with only the brightest stars resolved. Hubble changed everything. Its position above Earth's blurring atmosphere, combined with its exquisite optics, allowed astronomers to truly distinguish individual stars, from the brightest blue supergiants to the fainter, more numerous red giants and main sequence stars. This ability to resolve stars is crucial because it allows astronomers to create color magnitude diagrams for different regions of M31. These diagrams are like stellar family trees, plotting the brightness of stars against their color, which is related to their temperature, and revealing their ages, masses, and evolutionary stages. The drama of this data lies in its power to reconstruct M31's past.
By studying the distribution of different stellar populations, young, hot blue stars indicating recent star formation, and older, cooler, redder stars indicating ancient populations, astronomers can map out the galaxy's star formation history across its disk. Hubble's images have confirmed that M31 has experienced periods of intense star formation, particularly in its inner regions and within its prominent 10 kiloparsec ring. They also revealed older metal pore populations in the halo, consistent with the accretion of smaller galaxies throughout its history. Yet even with this incredible resolution, new questions emerge. Why do certain regions exhibit bursts of star formation while others remain relatively quiescent? How does the distribution of stellar ages and metallicities across M31 compared to that of the Milky Way? And what does this tell us about their differing evolutionary paths? The sheer volume of data from Hubble's PHAT survey is so immense that astronomers are still sifting through it, discovering new phenomena and refining their understanding of this cosmic titan. Hubble's gaze has not only illuminated M31, but has also deepened the sense of adventure and wonder surrounding its enduring mysteries.
The Andromeda Galaxy isn't just a static image in the night sky. It's a dynamic, evolving system, bearing the scars and triumphs of billions of years of cosmic history. Unraveling the story of M31's formation and evolution is akin to conducting galactic archaeology, sifting through stellar remnants and gas distributions to reconstruct its tumultuous past. This quest is fraught with challenges, as the forces that shaped this cosmic titan are complex and often leave subtle, enigmatic clues. What ancient cosmic events sculpted M31 into the grand spiral we observe today? And what profound implications do these insights hold for understanding galaxy formation across the universe? One of the most intriguing aspects of M31's past lies in its halo, the vast, diffuse region of stars and globular clusters that surrounds the main galactic disk. Observations of M31's halo, particularly using telescopes like Hubble and the Subaru telescope, have revealed a complex substructure, streams of stars, dwarf galaxies being tidally disrupted, and distinct populations of stars with different metallicities, their abundance of elements heavier than hydrogen and helium. These features are not random. They are the fossilized remains of smaller galaxies that M31 has gravitationally devoured over billions of years. Each stream and clump of stars represents a cosmic meal absorbed into the larger galaxy.
This process of hierarchical galaxy formation, where larger galaxies grow by accreting and merging with smaller ones, is a cornerstone of modern cosmology. M31 provides a living laboratory for studying this process firsthand. By mapping these stellar streams and analyzing the kinematics, which is the motions of the stars within them, astronomers can reconstruct the orbits of these devoured dwarf galaxies and even estimate when they were absorbed. This provides a direct, observational test of cosmological models, showing how galaxies assemble over cosmic time. The discovery of these tidal streams in M31's halo has been a dramatic confirmation of these theoretical predictions, offering a glimpse into the chaotic yet ultimately constructive nature of galactic growth. However, many questions remain. How many dwarf galaxies has M31 truly absorbed? What was their original size and composition? Are there hidden dwarf galaxies still in the process of being torn apart that we haven't detected yet? The faintness of these stellar streams make them incredibly challenging to observe, requiring the most sensitive telescopes and sophisticated data analysis techniques. Furthermore, understanding the precise dynamics of how a smaller galaxy is torn apart and assimilated by a larger one is a complex physics problem, involving gravitational interactions, dark matter distributions, and stellar feedback. The central bulge of M31 also holds clues to its formation. This dense, spheroidal region of old stars likely formed very early in the galaxy's history, perhaps through a violent merger event or a rapid collapse of primordial gas. But the exact sequence of events that led to the formation of both the bulge and the disk is still debated. Did the disk form first and then the bulge, or vice versa? Or did they co-evolve? M31, with its proximity and wealth of observational data, is a key piece of the puzzle, allowing astronomers to piece together the grand narrative of galactic evolution, from primordial gas clouds to the majestic spirals we see today.
The Andromeda Galaxy isn't an isolated entity. It's a central player in the local group, a cosmic neighborhood of over 80 galaxies, including our own Milky Way, the Triangulum Galaxy, M33, and numerous dwarf galaxies. Understanding the dynamics of this group and M31's dominant role within it is crucial for unraveling many of the remaining riddles surrounding our galactic neighbor. The gravitational ballet of the local group shapes M31's trajectory, its past interactions, and its ultimate destiny, offering profound insights into the evolution of galaxy clusters and the universe on larger scales. M31 is, by many measures, the largest member of the local group, although its exact mass compared to the Milky Way remains a point of contention, as we discussed. Regardless of the precise numbers, its gravitational influence is undeniable. It acts as a powerful gravitational attractor, pulling in smaller dwarf galaxies and influencing the motions of its larger companions. The two most prominent satellites of M31 are M32 and NGC 205, both elliptical dwarf galaxies that are gravitationally bound to Andromeda. Studies of these satellites, particularly their stellar populations and kinematics, can reveal a great deal about their interactions with M31 and provide indirect clues about Andromeda's dark matter halo. The most dramatic aspect of the local group's dynamics is, of course, the impending collision between M31 and the Milky Way. This gravitational dance is not just between two galaxies, but involves the entire local group. The smaller satellite galaxies of both M31 and the Milky Way will also be affected, potentially merging with the larger galaxies, being flung out into intergalactic space, or even captured by the newly formed Andromeda. The complex N-body simulations that model this collision must take into account the gravitational influence of all major members of the local group, making the predictions incredibly intricate.
Beyond the immediate collision, the local group provides a unique laboratory for cosmology. By studying the distribution and motions of galaxies within the local group, astronomers can test models of dark matter and dark energy, the mysterious components that dominate the universe's large-scale structure. The local group is a gravitationally bound system, meaning its expansion due to dark energy is relatively minor compared to the gravitational pull between its members. This makes it an ideal environment to study the interplay of gravity and the expansion of the universe on a smaller, more contained scale. Yet, many questions persist about the local group's formation and evolution. How did the initial distribution of dark matter and baryonic matter lead to the specific configuration of galaxies we see today? Are there hidden dwarf galaxies within the local group that have yet to be discovered? The very existence of such a compact, gravitationally bound group of galaxies within an expanding universe is a testament to the power of cosmic gravity, and M31 stands at its heart, a central figure in a cosmic drama that continues to unfold. Understanding its place in the local group is essential to truly grasping the full extent of its mysteries.
One of the most profound and persistent mysteries surrounding the Andromeda Galaxy, and indeed every large galaxy, is the pervasive and enigmatic presence of dark matter. We cannot see it, it doesn't emit or absorb light, yet its gravitational influence is undeniably woven into the very fabric of galactic dynamics.
For M31, the question of its dark matter content isn't just an academic exercise. It's fundamental to understanding its true mass, its rotational dynamics, and its future interaction with the Milky Way. What is this invisible scaffolding that holds Andromeda together, and how does its elusive nature complicate our quest to truly understand this cosmic titan? The evidence for dark matter in M31 comes primarily from observations of its rotational curve. If galaxies were composed only of the visible matter, stars, gas, and dust, their rotational speeds should decrease significantly as one moves further from the galactic center, just like planets orbit the sun more slowly the further out they are. However, when astronomers measure the rotational speeds of stars and gas in M31's outer disk, they find that these speeds remain remarkably constant or even increase slightly far beyond where visible matter alone could account for the gravitational pull. This discrepancy implies that there must be a vast, unseen halo of mass extending far beyond the visible disk, providing the additional gravitational force needed to keep the outer regions rotating so quickly. This invisible mass is what we call dark matter. Estimates suggest that dark matter constitutes roughly 85% of the total mass of M31, meaning that for every kilogram of visible stars and gas, there are many more kilograms of this mysterious substance. This overwhelming dominance of dark matter shapes the galaxy's overall gravitational potential, influencing the orbits of its stars and satellite galaxies and dictating the scale of its gravitational well. The precise distribution of this dark matter halo within M31 is a subject of intense research. Is it a smooth, spherical halo, or does it have substructures, perhaps remnants of smaller dark matter halos from accreted dwarf galaxies? The answer has profound implications for our understanding of dark matter itself and how it interacts with visible matter during galaxy formation.
The drama of this quest lies in the very nature of dark matter. We can only infer its presence through its gravitational effects. Scientists are constantly devising new observational techniques and theoretical models to probe its distribution. For instance, the motions of globular clusters in M31's halo can provide clues about the extent and shape of its dark matter halo. Similarly, the kinematics of M31's dwarf satellite galaxies, like M32 and NGC 205, are strongly influenced by the dark matter potential of their host galaxy. Analyzing these subtle gravitational tugs helps astronomers build more accurate maps of this invisible component. However, the nature of dark matter itself remains one of the greatest unsolved riddles in physics. Is it composed of weakly interacting massive particles, WIMPs, axions, or something entirely exotic? While experiments on Earth tried to detect dark matter particles directly, astronomical observations of galaxies like M31 provide crucial insights into its properties on cosmic scales. The elusive veil of dark matter surrounding Andromeda is not just a local mystery, it's a window into the fundamental composition of the universe, compelling us to push the boundaries of our scientific understanding.
When astronomers talk about the total mass of a galaxy like M31, they often refer to its virial mass. This concept is crucial because it accounts for the total gravitational potential of the galaxy, including its dominant dark matter halo, by examining the motions of objects gravitationally bound to it. Understanding the virial mass of the Andromeda galaxy is not only a key component in precisely weighing this cosmic titan, but also a dramatic battleground in the ongoing scientific effort to comprehend the true extent and influence of dark matter. How do we measure the invisible, and what does this virial mass truly tell us about the dark matter's embrace? The virial theorem in astrophysics provides a powerful tool for estimating the total mass of a gravitationally bound system in equilibrium, such as a galaxy or a galaxy cluster. It relates the kinetic energy of the system's components, stars, gas, dark matter particles, to its potential energy. In simpler terms, if a galaxy is stable, the outward pressure from the motion of its constituents must be balanced by the inward pull of gravity. By measuring the velocities of objects orbiting within and around M31, from individual stars in its outer disk to its numerous satellite galaxies, astronomers can infer the total mass enclosed within a certain radius, including the unseen dark matter. This is particularly effective for estimating the mass of the galaxy's halo, where dark matter is expected to be most abundant.
For M31, various studies have attempted to determine its viral mass, and the results have often been a source of significant debate and refinement. Early estimates of M31's viral mass, often based on the velocities of its brightest satellite galaxies and globular clusters, suggested it was significantly more massive than the Milky Way, perhaps up to 2 trillion solar masses. This made M31 the undisputed heavyweight of the local group. However, more recent, precise measurements and improved modeling techniques have led to a narrowing of this discrepancy. Some studies, particularly those published around 2018-2019, using sophisticated simulations and kinematic data from the Gaia mission, have indicated that M31's viral mass might be closer to that of the Milky Way, perhaps around 1 to 1.5 trillion solar masses. This ongoing revision of M31's virial mass highlights the challenges of dark matter research. The uncertainties arise from several factors: the difficulty in precisely measuring the three-dimensional velocities of distant objects, the assumption of virial equilibrium, which may not always hold perfectly true, and the complex interplay of dark matter with baryonic matter. For example, the phenomenon of adiabatic contraction, where baryonic matter collapsing to form a galaxy pulls dark matter inward, can significantly alter the dark matter density profile, impacting virial mass estimates. The stakes are high. A more massive M31 would mean a stronger gravitational pull on the Milky Way, potentially altering the timeline and nature of their future collision. It would also imply a different history of dark matter accretion and distribution within the local group. The dramatic hunt for M31's true virial mass is a quest to quantify the invisible, to weigh a cosmic ghost that nonetheless dictates the destiny of galaxies, providing invaluable insights into the fundamental architecture of the universe. As we anticipate the dramatic collision between the Andromeda Galaxy and our own Milky Way, it's crucial to understand that this isn't just a merger of stars and gas. It's fundamentally a collision of colossal dark matter halos. The invisible, dominant component of both galaxies will dictate the gravitational dance, shaping the trajectory, the energy dissipation, and the ultimate fate of this galactic encounter. How does this elusive substance orchestrate one of the grandest cosmic ballets, and what new riddles does its influence present for our understanding of galactic mergers? Imagine two immense invisible spheres, each many times larger than the visible galaxy within it, hurtling towards each other. These are the dark matter halos of M31 and the Milky Way. When the two visible galactic disks first begin to interact, their dark matter halos will already have been passing through each other for millions of years. Unlike stars, which are largely point-like and rarely collide, dark matter particles are theorized to be collisionless or very weakly interacting. This means they will largely pass through each other during the merger, experiencing only mutual gravitational attraction. This fundamental difference in behavior between dark matter and baryonic matter has profound implications for the collision. The immense gravitational potential created by these passing dark matter halos will act as a powerful braking mechanism, gradually slowing down the two galaxies and drawing them closer together. This gravitational friction, often referred to as dynamic friction, is key to the merger process. Without the dark matter halos, the galaxies might simply fly past each other after an initial encounter, rather than spiraling inwards and coalescing into a single entity.
The extent and density of each galaxy's dark matter halo will directly influence the efficiency of this dynamic friction, thus dictating the precise timeline and the number of passes before the full merger.
Computer simulations of galactic collisions, which are essential tools for predicting the outcome of the M31 Milky Way encounter, critically depend on the assumed distribution and properties of dark matter. If the dark matter halos are more centrally concentrated, the merger might proceed more quickly. If they are more diffuse, the process could be more drawn out. These simulations also allow astronomers to explore what happens to the dark matter itself during such a colossal event. Will the merged galaxy have a larger, more massive dark matter halo? Will the distribution of dark matter be significantly altered, perhaps becoming more spherical or clumpy? The drama of this cosmic encounter lies not only in the visible spectacular changes, but also in the invisible reshaping of the universe's fundamental architecture. Studying the predicted outcome of the Milkometa merger offers a unique opportunity to test our theories about dark matter's properties and its role in galaxy evolution. For instance, if dark matter were to interact more strongly with itself than currently believed, the collision might lead to different observable effects. By observing similar mergers in the distant universe, astronomers can compare them to our predictions for Milkometa, refining our understanding of this most enigmatic substance. The collision of Andromeda and the Milky Way is not just a future spectacle. It's a cosmic experiment in dark matter dynamics, poised to unravel some of its deepest secrets.
At the very heart of the Andromeda Galaxy lies a colossal secret, a supermassive black hole known as P2, believed to be millions, if not tens of millions, of times the mass of our Sun. Like the supermassive black hole Sagittarius A at the center of our own Milky Way, this gravitational behemoth is the silent, powerful engine around which the entire galaxy orbits. Yet, despite its immense influence, probing the depths of M31's core and understanding its central black hole presents a formidable challenge, shrouded in layers of dust, gas, and an extraordinary density of stars. What mysteries does this luminous enigma hold, and how does it impact the galaxy around it? Observations using the Hubble Space Telescope and ground-based observatories have allowed astronomers to measure the velocities of stars orbiting incredibly close to M31's very center. By applying Kepler's laws of planetary motion on a galactic scale, they can infer the presence of an enormous, unseen mass concentrated in a tiny volume, the unmistakable signature of a supermassive black hole. Early estimates placed its mass around 30 million solar masses, though more refined measurements and dynamical models have sometimes suggested values closer to 100 million solar masses, highlighting the ongoing uncertainty in precisely weighing these cosmic leviathans.
The region immediately surrounding M31's central black hole is known as its nuclear star cluster. This is one of the densest stellar environments in the universe, with stars packed together far more tightly than anywhere else in the galaxy. This extreme stellar density, combined with vast amounts of obscuring dust, makes direct observation of the black hole itself incredibly difficult. We cannot see a black hole directly, only its effects on the surrounding matter. When gas and dust spiral inwards toward the black hole, they form an incredibly hot, luminous accretion disk, emitting powerful X-rays and radio waves. While M31's central black hole is currently relatively quiescent, its past activity is etched into the surrounding environment.
One of the most perplexing features of M31's core is its enigmatic double nucleus. For many years, observations suggested two distinct bright spots at the very center of the galaxy. Was this evidence of two supermassive black holes, or something even more exotic? Subsequent, higher-resolution observations, again largely thanks to Hubble, revealed that this double nucleus is likely an optical illusion. It's believed to be a single, massive disk of stars orbiting the black hole, with a portion of the disk obscured by dust making it appear as two distinct lobes. However, the precise dynamics of this eccentric stellar disk and its interaction with the black hole are still subjects of active research. The supermassive black hole at the heart of Andromeda is not merely a gravitational anchor, it's also a crucial component in the galaxy's evolution. Its powerful gravitational influence can affect the motions of stars, trigger star formation, or suppress it, and even launch powerful jets of material that can shape the surrounding galactic environment. Understanding the precise mass, spin, and accretion history of M31's central black hole is vital for completing our picture of this cosmic titan, offering profound insights into the coevolution of galaxies and their central engines.
The unresolved riddles of the Andromeda Galaxy are a powerful impetus for the development of next-generation astronomical observatories. While telescopes like Hubble have revolutionized our understanding, new instruments, both on Earth and in space, promise to push the boundaries of discovery even further. The dramatic unveiling of M31's deepest secrets will undoubtedly be aided by these future eyes, offering unprecedented clarity, sensitivity, and wavelength coverage. What new frontiers will these advanced observatories allow us to explore? And how will they fundamentally reshape our comprehension of this cosmic neighbor?
One of the most anticipated ground-based observatories poised to make significant contributions to M31 studies is the Vera C. Rubin Observatory, formerly LSST, Large Synoptic Survey Telescope. While not designed for deep, high-resolution imaging of individual stars like Hubble, Rubin will revolutionize our understanding of transient phenomena, including novae, supernovae, and microlensing events within M31. Its wide field of view and rapid survey capabilities will allow it to scan the entire Andromeda Galaxy repeatedly every few nights. This unprecedented cadence will enable astronomers to detect new transients almost as they happen, providing crucial data on stellar evolution, binary systems, and even potential exoplanet transits, though extremely challenging, within M31. Imagine a continuous, real-time cosmic movie of M31, revealing dynamic changes that are currently missed by less frequent observations. Another game-changer will be the James Webb Space Telescope, JWST. While JWST is primarily optimized for observing the early universe in infrared light, its incredible sensitivity and resolution in these wavelengths will provide unparalleled views of M31. Infrared light penetrates dust more effectively than visible light, allowing JWST to peer into obscured star-forming regions within M31's disk, and even closer to its dusty, crowded galactic center. This will enable detailed studies of protoplanetary disks, very young stars, and the dusty environment surrounding them. Furthermore, JWST's spectroscopic capabilities will allow for precise measurements of the chemical compositions of stars and gas in M31, offering deeper insights into its metallicity gradients and star formation history, potentially resolving mysteries about the efficiency of star birth in different galactic environments.
Looking further ahead, the Nancy Grace Roman Space Telescope, formerly known as W-FIRST, will also be invaluable. This wide-field infrared survey telescope will be capable of mapping vast areas of the sky with Hubble-like resolution. For M31, Roman will be able to survey an even larger portion of the galaxy than Hubble's PHAT survey, identifying millions more individual stars and mapping the distribution of dark matter through gravitational lensing techniques with greater precision. It could detect even fainter tidal streams in M31's halo, revealing more about its accretion history. The dramatic promise of these future observatories lies in their complementary capabilities. By combining the rapid survey power of Rubin, the infrared penetration and spectroscopic prowess of JWST, and the wide-field high-resolution mapping of Roman, astronomers will gain a multifaceted view of M31. This integrated approach will undoubtedly unravel many of the remaining riddles, from precisely weighing its dark matter halo to understanding the intricacies of star formation in its barred spiral structure, pushing the boundaries of what we can know about our cosmic neighbor.
The ultimate quest of cosmic exploration often leads to the profound question, are we alone? While the search for extraterrestrial life has largely focused on exoplanets within our own Milky Way, the Andromeda Galaxy, with its estimated trillion stars, offers a tantalizing, yet largely unexplored, frontier for astrobiology. Could life, perhaps even advanced civilizations, have arisen on planets orbiting distant suns in this neighboring cosmic titan? The idea presents both thrilling possibilities and immense challenges, adding a dramatic, philosophical dimension to the riddles of M31. The foundational requirement for life as we know it is the presence of liquid water. This necessitates planets orbiting their stars within the habitable zone, where temperatures are just right for water to remain in liquid form. Given the sheer number of stars in M31, statistically, it's highly probable that a significant number of them host planetary systems, and a fraction of those planets could reside in their star's habitable zone. Could these conditions have led to the emergence of life, perhaps even life that adapted to the unique astrophysical environments of a larger, more densely packed galaxy?
However, detecting exoplanets in a galaxy 2.5 million light-years away is an extraordinary challenge, far beyond our current technological capabilities. Current exoplanet detection methods, such as the transit method, observing dips in a star's brightness as a planet passes in front of it, or the radio velocity method, detecting wobbles in a star's motion caused by an orbiting planet, rely on extremely precise measurements of individual stars. Resolving individual stars in M31 well enough to detect these subtle changes is currently impossible, even with the most powerful telescopes. The vast distance means that the light from individual stars is extremely faint, and they are hopelessly blended together even in our best images. So, how might we even begin to search for life or biosignatures in M31? The approach would likely have to be indirect and highly speculative at this stage. One hypothetical method involves searching for technosignatures, indicators of advanced technology. For instance, extremely powerful directed radio signals that are clearly artificial might be detectable across intergalactic distances, though the sheer power required would be immense. Another speculative possibility involves searching for evidence of Dyson spheres or other megastructures that could alter a star's light in ways that would be observable even from millions of light-years away. These are, of course, highly theoretical and at the very edge of scientific speculation, bordering on science fiction. The astrobiological implications of M31 also extend to the future galactic collision. If life exists in Andromeda, what would its fate be during the Milky-Meta merger? Would planetary systems be disrupted, or would they simply find themselves in a new, more chaotic galactic environment? The philosophical drama is profound. Could future descendants of humanity one day encounter alien life forms that originated in M31, brought together by the very forces of cosmic evolution? While a direct search for M31 exoplanets remains a distant dream, the contemplation of life beyond our galactic shores underscores the profound and thrilling potential for discovery that lies within the Andromeda Galaxy.
The Andromeda Galaxy, this radiant cosmic titan, was not discovered in a single dramatic moment by a lone astronomer. Instead, its recognition as a distinct celestial object evolved over centuries, a testament to humanity's persistent curiosity and improving observational tools. The story of its early observations, from ancient Persian texts to the diligent cataloging of Charles Messier, reveals a fascinating progression from a faint little cloud to a recognized nebula, laying the groundwork for the profound scientific debates that would eventually uncover its true nature. What did these early stargazers see, and how did their limited observations inadvertently set the stage for one of the greatest paradigm shifts in cosmic understanding? One of the earliest recorded observations of what we now know as the Andromeda Galaxy dates back to the year 964 CE. The Persian astronomer Abd al-Rahman al-Sufi, in his monumental book of fixed stars, meticulously described a small cloud or nebulous patch near the constellation Andromeda. He explicitly noted it as being distinct from stars, calling it al-Latma, or the blotch. Al-Sufi's work was based on direct naked-eye observations, a remarkable feat given the faintness of M31, visible only under very dark skies. His record demonstrates an acute observational skill and an early recognition of non-stellar objects, pushing the boundaries of astronomical description at the time. Centuries later, with the invention of the telescope, observations of the Andromeda Nebula became more widespread, though its true nature remained a mystery. Simon Marius, in 1612, was one of the first Europeans to observe it telescopically, describing it as resembling a flame of a candle when seen through his rudimentary instrument. He noted its fuzzy appearance, distinct from the sharp points of stars, further solidifying its classification as a nebula, a Latin word for cloud.
The systematic cataloging of nebulae and star clusters truly took off in the 18th century, largely thanks to the meticulous work of French astronomer Charles Messier. His primary goal was to create a catalog of fuzzy objects that might be mistaken for comets, which were his true passion. In 1764, Messier added the Andromeda Nebula to his renowned catalog as M31, the 31st entry. He described it simply as a nebula without stars, recognizing its diffuse nature but still unaware of its immense distance or stellar composition. Messier's catalog, while born from practical necessity, became an invaluable resource for future astronomers, standardizing the nomenclature for many deep sky objects, including Andromeda. These early observations, from Al-Sufi's little cloud to Messier's nebula without stars, represent the initial, cautious steps in humanity's quest to understand the universe beyond the stars. They were observations of wonder and curiosity, made without the benefit of modern physics or grand cosmological models. Yet they planted the seeds for the dramatic debates and revolutionary discoveries of the 20th century, culminating in the realization that this humble blotch was in fact an entire island universe, a galactic twin to our own. The journey from a faint smudge to a cosmic titan is a testament to the power of persistent human inquiry.
The early 20th century marked a pivotal turning point in our understanding of the universe, and the Andromeda Galaxy once again played a starring role. While its appearance as a nebula was long established, its true nature, whether it was a cloud within our own galaxy or a separate island universe, remained one of astronomy's most profound, unresolved riddles. The dramatic breakthrough came from the pioneering work of American astronomer Vesto Slipher, who through meticulous measurements of the Doppler shift revealed Andromeda's astonishing motion, forever altering our perception of the cosmos. In 1912, at the Lowell Observatory in Flagstaff, Arizona, Slipher embarked on a systematic study of the spectra of various spiral nebulae. He was interested in measuring their radial velocity, how fast they were moving towards or away from Earth. This is achieved by observing the Doppler shift in their light. Just as the pitch of an ambulance siren changes as it approaches and then recedes, the wavelength of light from a celestial object shifts depending on its motion. If an object is moving towards us, its light waves are compressed, shifting towards the blue end of the spectrum, blue shift. If it's moving away, the waves are stretched, shifting towards the red end, red shift.
Slipher's work was incredibly painstaking. Early spectrographs were inefficient, and the light from these faint nebulae was incredibly dim, requiring exposures lasting many hours, sometimes over several nights. Imagine the dedication required to collect enough photons to create a measurable spectrum. When he finally analyzed the spectrum of the Andromeda Nebula, his results were nothing short of revolutionary. He found a significant blue shift, indicating that M31 was approaching our Sun at an unprecedented speed of approximately 300 kilometers per second, or about 186 miles per second. This measurement was utterly astonishing. At the time, all other nebulae Slipher had observed showed redshifts, meaning they were moving away from us. Andromeda was the lone exception, a cosmic anomaly. More importantly, its speed was far greater than any star known to exist within the Milky Way. If M31 were simply a cloud of gas within our galaxy, it wouldn't be moving at such an extraordinary velocity relative to galactic rotation. Slipher's findings provided the first strong kinematic evidence that the Andromeda Nebula was not merely a local cloud, but a truly immense object, moving independently of our galaxy's general stellar motions. The drama of Slipher's revelation cannot be overstated. It was a crucial piece of the puzzle that would eventually confirm the island universe theory. While it didn't directly prove the immense distance to M31, it showed that it was an independent cosmic entity, not bound by the Milky Way's dynamics. Slipher himself remained cautious in his interpretations, but his work profoundly influenced the astronomers who followed, particularly Edwin Hubble, who would later use Cepheid variable stars to definitively measure Andromeda's distance. Slipher's painstaking measurement of the Doppler shift in M31's light was not just a scientific observation, it was a cosmic premonition, foreshadowing the collision to come and fundamentally reshaping humanity's place in an ever-expanding, dynamic universe.
The Andromeda Galaxy, or more precisely, the Andromeda Nebula, was at the very heart of one of the most significant intellectual battles in the history of astronomy, the Great Debate of 1920. This dramatic confrontation pitted two titans of American astronomy, Harlow Shapley and Heber D. Curtis, against each other at the National Academy of Sciences in Washington, D.C., arguing over the fundamental scale and structure of the universe. At stake was nothing less than humanity's understanding of its cosmic address. Was our Milky Way galaxy the entirety of the universe? Or were spiral nebulae like Andromeda independent island universes far beyond its bounds? Harlow Shapley, an influential astronomer at Mount Wilson Observatory, championed the view that the Milky Way was the entire universe, and that all spiral nebulae, including Andromeda, were merely gas clouds or protoplanetary systems within its confines. His arguments were based on several points. He had accurately mapped the size of the Milky Way, placing our solar system far from its center, and he believed that the globular clusters, which he had used as distance indicators, were uniformly distributed throughout our galaxy, arguing that no object could be beyond its immense reach. He also cited the incredible apparent brightness of novae observed in Andromeda, like Curtis's S Andromedae, arguing that if it were truly extragalactic, its absolute luminosity would be impossibly high. Heber D. Curtis, director of the Allegheny Observatory, countered vehemently with the island universe hypothesis. He argued that spiral nebulae were indeed separate galaxies, analogous to our own. His primary evidence included the higher number of novae observed in Andromeda than in the Milky Way, which he believed was more consistent with an independent galaxy containing vast numbers of stars. He also pointed to the presence of dark lanes in spiral nebulae, which resembled the dust lanes observed within the Milky Way, suggesting similar structures. Crucially, Curtis had also made observations of faint nova-like objects in Andromeda, which we now know were supernovae, vastly more luminous than novae, further strengthening his argument for immense distances. The dramatic tension of the debate was palpable, as each astronomer presented compelling, yet ultimately incomplete evidence.
The debate ended without a definitive victor, as the available evidence was still insufficient to conclusively prove either side. However, the intellectual ferment it generated was immense.
It laid bare the crucial questions that needed to be answered and spurred astronomers to develop new methods for measuring cosmic distances. The outcome, as history would reveal, favored Curtis's general hypothesis, but it took further groundbreaking work to definitively settle the matter. The resolution came just a few years later, primarily through the efforts of Edwin Hubble. Using the newly completed 100-inch Hooker telescope at Mount Wilson, Hubble was able to identify and measure Cepheid variable stars in the outer regions of M31. These pulsating stars have a direct relationship between their pulsation period and their intrinsic luminosity, making them incredibly reliable standard candles for measuring cosmic distances. Hubble's measurements unequivocally showed that M31 was indeed millions of light years away, far beyond the furthest reaches of the Milky Way. This dramatic discovery, announced in 1925, decisively ended the Great Debate, forever transforming humanity's view of the universe from a single island galaxy to a vast cosmic archipelago of billions of galaxies.
The Andromeda Galaxy's iconic spiral arm structure is not merely a beautiful cosmic aesthetic, it's a dynamic, evolving feature that holds profound secrets about the galaxy's rotation, star formation processes, and even its past interactions. Understanding the intricate dance of these spiral arms and the mechanisms that sustain them is another major unresolved riddle. How do these grand patterns emerge and persist over billions of years? And what do their specific characteristics tell us about the internal dynamics of this colossal barred spiral? M31 is classified as a barred spiral galaxy, meaning it possesses a central bar-shaped structure of stars from which its spiral arms emanate. Unlike the Milky Way, whose spiral arms are often described as grand and clearly defined, Andromeda's arms are somewhat more tightly wound and less distinct in some regions, appearing almost flocculent in places. They are typically traced by the presence of young blue stars and H2 regions where intense star formation is occurring. However, mapping the precise three-dimensional structure of these arms and understanding how they are maintained is a complex challenge. The prevailing theory for the formation of spiral arms is the density wave theory. This theory proposes that spiral arms are not fixed material structures like spokes on a wheel, but rather regions of enhanced density that propagate through the galactic disk, similar to a traffic jam on a highway. As stars and gas orbit the galactic center, they encounter these density waves, slow down, compress, and then move out of the wave. This compression of gas can trigger the collapse of molecular clouds and ignite new star formation, explaining why spiral arms are often luminous with young, hot stars.
However, applying the density wave theory to M31 presents its own set of riddles. What specific mechanisms are driving these density waves? Are they sustained by the galaxy's central bar, or perhaps by gravitational interactions with its satellite galaxies? The precise pitch angle of M31's spiral arms, their number, and their longevity are all crucial parameters that can inform theoretical models. Observations reveal that M31 has a relatively well-defined 10 kiloparsec ring, which is often interpreted as a primary star-forming ring, potentially a result of a resonance with the bar or a past interaction. Why this ring is so prominent and how it relates to the broader spiral structure is a subject of ongoing debate. Furthermore, the dynamics of gas within these spiral arms are incredibly complex. Gas is not only compressed by the density waves, but also influenced by stellar feedback, supernova explosions pushing gas out, and magnetic fields. This intricate interplay dictates where and when new stars are born, leading to the patchy, uneven star formation observed in M31. The exact role of the central bar in channeling gas and influencing the spiral pattern is still being refined. How much gas does it funnel inwards? How does this affect the star formation rates in the inner versus outer parts of the disk? The dramatic and beautiful spiral arms of Andromeda are more than just a visual feast. They are dynamic puzzles, their complex motions and ephemeral nature challenging our understanding of galactic self-organization. By studying M31's spiral structure, astronomers aim to unravel not just the mysteries of this particular galaxy, but the fundamental processes that shape all spiral galaxies across the universe.
The Andromeda Galaxy's impending collision with the Milky Way isn't just a dramatic future event. It's an unprecedented opportunity to study galaxy mergers in exceptional detail. As the closest major example of such a monumental cosmic event, M31 offers a unique laboratory for understanding the physical processes that drive galaxy mergers and their profound implications for galaxy evolution and cosmology. What insights does M31, as both a participant and a model, provide into these titanic collisions, and what mysteries do these interactions continue to present? Galaxy mergers are fundamental drivers of galactic evolution. They are believed to be responsible for the growth of massive galaxies, the formation of elliptical galaxies from spiral progenitors, the triggering of bursts of star formation, and the growth of supermassive black holes at galactic centers. However, observing these events in the distant universe often provides only snapshots in time, making it difficult to reconstruct the full evolutionary sequence. M31, by virtue of its proximity and its well-characterized approaching trajectory, offers a unique before picture for a future merger, allowing astronomers to make detailed predictions and test their models.
The study of M31's past interactions with its own satellite galaxies already provides crucial insights into merger processes. We've discussed the tidal streams in its halo, the ghostly remnants of smaller galaxies that M31 has absorbed over billions of years. By analyzing the kinematics and stellar populations of these streams, astronomers can infer the properties of the devoured galaxies and the timeline of their accretion. This galactic archaeology informs our understanding of how galaxies grow through hierarchical merging. The dramatic disruption of these smaller systems as they are torn apart by M31's immense gravity offers real-world examples of tidal forces at play during a merger. Furthermore, M31 serves as a crucial testbed for N-body simulations of galaxy mergers. These sophisticated computer models simulate the gravitational interactions of billions of particles, representing stars, gas, and dark matter, as two galaxies collide. By inputting the observed properties of M31 and the Milky Way, mass, size, dark matter distribution, relative velocity, these simulations can predict the various phases of the merger, the initial close passes, the stripping of gas and stars, the eventual coalescence, and the formation of a new, larger galaxy. The accuracy of these simulations depends heavily on our understanding of the underlying physics, particularly the behavior of dark matter and baryonic matter during strong gravitational encounters. One of the key riddles that M31's impending merger helps address is the fate of gas and star formation during a collision. Will the compression of gas clouds lead to a massive burst of star formation, as is often seen in distant merging galaxies? Or will the violent interactions primarily lead to gas being stripped away or heated, inhibiting star birth? The simulations for the Andromeda merger suggest that while there might be some localized star formation, the overall effect might be less dramatic than some other mergers, perhaps due to the relatively low gas content in the outer disks of both galaxies.
The dramatic narrative of M31's journey towards the Milky Way is not just a story of a cosmic collision, it's a living textbook on galaxy mergers, providing invaluable insights into one of the most fundamental processes that shapes the universe. Every observation of M31 today contributes to our predictive power for this grand cosmic event, offering a rare opportunity to witness, in slow motion, the very evolution of galaxies.
The impending collision between the Andromeda Galaxy and our own Milky Way, though billions of years in the future, forces us to confront profound philosophical questions about humanity's place in a dynamic, evolving universe. This cosmic drama isn't just a scientific prediction, it's a powerful narrative that challenges our sense of stability and permanence, inviting us to reflect on our cosmic destiny. What does it mean for our future, for our identity, to be part of a galaxy destined for such a monumental transformation? For centuries, humanity has viewed the stars as eternal and unchanging, a fixed backdrop against which our fleeting lives play out. The realization that galaxies themselves are dynamic entities capable of immense transformations shatters this perception. The Andromeda collision reminds us that the universe is not static, it is constantly in motion, evolving on scales far beyond human comprehension. This perspective can be both humbling and exhilarating. It underscores our transient nature in the grand scheme of cosmic time, yet it also highlights our unique position as beings capable of understanding and predicting such colossal events.
Consider the dramatic implications for future civilizations, perhaps billions of years from now. If humanity or its descendants still exists on Earth, or beyond, having colonized other worlds, what would their night sky look like? The familiar constellations would be unrecognizable, distorted by the gravitational forces of the merging galaxies. New, brilliant bursts of star formation might illuminate the sky, and perhaps the merging supermassive black holes would create awe-inspiring flares of energy. This forces us to imagine a future where the very canvas of our existence undergoes a radical, irreversible change. This impending collision also compels us to think about the nature of our galactic identity. We identify as inhabitants of the Milky Way, a spiral galaxy with distinct characteristics. But in 4.5 billion years, that identity will dissolve into something new, a larger, likely elliptical galaxy, a cosmic hybrid. Does our connection to the Milky Way extend beyond its current form? Does our future identity become Milko-Maiden? This transformation is a powerful metaphor for change on an unimaginable scale, echoing themes of impermanence and adaptation that resonate throughout human experience. Furthermore, the collision prompts reflection on humanity's ultimate fate. While the probability of direct stellar collisions is negligible, the gravitational perturbations could potentially alter stellar orbits, perhaps even flinging our solar system into the vast emptiness of intergalactic space, or drawing it closer to the galactic core. These are dramatic possibilities, yet they also highlight the resilience and adaptability of life, suggesting that even in the face of galactic-scale upheaval, there might be pathways for survival and continued evolution. The philosophical implications extend beyond our species. If life exists elsewhere in Andromeda, how would it experience this merger? Would different forms of life respond to these cosmic changes in unique ways? The contemplation of such questions expands our sense of wonder and deepens our appreciation for the intricate, dynamic tapestry of the cosmos. The Andromeda Galaxy's journey towards us is more than just a scientific prediction. It's a cosmic saga that challenges us to imagine our place in a universe of continuous, dramatic transformation. To truly appreciate the unique, unresolved riddles of the Andromeda Galaxy, it's essential to place it in context, specifically through a comparative analysis with our own home galaxy, the Milky Way. While both are grand barred spiral galaxies and the dominant members of the local group, subtle and sometimes dramatic differences between them highlight the vast diversity even within similar galactic classifications and offer clues to their distinct evolutionary paths. What sets these two cosmic titans apart, and what can their contrasting features tell us about galaxy formation and evolution more broadly? Perhaps the most debated difference lies in their mass and stellar content. For a long time, M31 was considered significantly more massive than the Milky Way, boasting perhaps 1 trillion stars compared to our galaxy's estimated 200 to 400 billion.
This would make M31 the clear heavyweight champion of the local group. However, as discussed, recent studies have narrowed this gap, with some suggesting their masses are quite comparable, or even that the Milky Way might be slightly more massive in terms of dark matter. This ongoing debate underscores the challenge of precisely weighing galaxies and the subtle complexities of dark matter distribution. Regardless of the exact numbers, M31 undeniably has a larger stellar population, meaning more stars packed into its disk and bulge. Another key difference lies in their spiral arm structure and star formation rates. The Milky Way is often described as having more prominent, grand design spiral arms, particularly in its inner regions, with significant star formation activity spread across its disk. M31, while also a barred spiral, tends to have more tightly wound, flocculent arms, and its star formation appears to be more concentrated in a prominent 10 kiloparsec ring and its outer regions, with a relatively quiet inner disk and bulge. Why this difference? It could be due to differing gas content, past merger histories, or the precise nature of their central bars and density waves. This divergence in star formation patterns is a major riddle, hinting at distinct evolutionary processes. Their central supermassive black holes also show intriguing differences. While both galaxies host colossal black holes, M31's central black hole, P2, is generally estimated to be more massive than the Milky Way's Sagittarius A star, perhaps by a factor of 10 to 20, around 10 to the 8th solar masses for M31 versus 4 times 10 to the 6th solar masses for SGR A star. This difference in central black hole mass relative to the galaxy's stellar mass can offer insights into the coevolution of black holes and their host galaxies, a topic of intense research. Additionally, M31's enigmatic double nucleus is a feature not observed in the Milky Way, hinting at unique past dynamics near its core.
Finally, their satellite galaxy populations also differ. M31 has a more numerous and diverse collection of satellite galaxies, including the relatively large dwarf ellipticals M32 and NGC 205, which are visible in even small telescopes. The Milky Way has its own retinue of dwarf galaxies, including the large and small Magellanic Clouds, but its overall satellite system is generally considered less numerous and less massive than M31's. This difference in satellite populations is a direct consequence of their accretion mysteries, providing clues about which galaxy has eaten more smaller galaxies over cosmic time. The comparative analysis of M31 and the Milky Way is more than just a side-by-side comparison. It's a dramatic exploration of galactic diversity and evolution. By contrasting their similarities and differences, astronomers gain deeper insights into the myriad paths galaxies can take as they grow and evolve within the vast, dynamic cosmos.
Beyond the familiar bright spiral arms and bustling galactic core, the Andromeda Galaxy extends into vast, diffuse, and enigmatic regions, its expansive disk, and its even larger ethereal halo. Probing these extreme frontiers of M31 is crucial for unraveling many of its deepest mysteries, from its total mass and dark matter distribution to its accretion history. What hidden secrets do these far-flung stellar populations and gas reservoirs hold, and how do they challenge our observational capabilities? The disk of M31, though appearing as a relatively flat plane, actually has a complex three-dimensional structure. Observations have revealed that it is not perfectly flat, but exhibits a subtle warp, likely caused by gravitational interactions with its satellite galaxies or even the Milky Way itself. Understanding the extent and nature of this warp is important for modeling the galaxy's dynamics and its future collision. The outer reaches of the disk, where star formation often continues, transition into a more diffuse environment, the outer disk, where stellar densities decrease dramatically. Studying the stars in these sparse regions can reveal clues about the galaxy's chemical evolution and the efficiency of star formation in low-density environments.
Beyond the visible disk lies the true enigma, M31's stellar halo. This vast, roughly spherical region extends far beyond the bright spiral arms, stretching for hundreds of thousands of light years. It is sparsely populated with individual stars, ancient globular clusters, and the ghostly remnants of smaller dwarf galaxies that M31 has gravitationally devoured over billions of years. These tidal streams and stellar shells are like cosmic archaeological artifacts, preserving the history of Andromeda's violent growth through accretion. Each stream represents a meal for the massive galaxy, a smaller system torn apart by immense tidal forces and absorbed into M31's growing halo. Observing the halo is incredibly challenging due to its extreme faintness and diffuse nature. It requires long exposure times with powerful telescopes like Hubble and the Subaru telescope, often using specialized filters to highlight particular stellar populations. The drama of this observational quest lies in the painstaking effort to detect faint, isolated stars and trace their motions, revealing the invisible architecture of galactic mergers. By mapping the kinematics of these halo stars, astronomers can infer the presence and distribution of dark matter, as the halo is believed to be predominantly composed of this elusive substance.
Furthermore, the halo's chemical composition can provide insights into M31's very early formation. Stars in the halo are generally very old and metal-poor, meaning they contain very few elements heavier than hydrogen and helium. This suggests they formed early in the universe's history, before significant amounts of heavy elements were forged in the cores of massive stars and dispersed by supernovae. By studying these pristine stellar populations, astronomers can gain a glimpse into the conditions of the early universe and how the first stars and galaxies assembled. The boundaries of the disk and halo are not sharply defined. They are fluid, dynamic regions shaped by gravity, mergers, and stellar feedback. Probing these extreme regions of M31 is a dramatic frontier of modern astronomy, pushing the limits of our observational capabilities and revealing the full extent of this cosmic titan and its tumultuous history.
The stars within the Andromeda Galaxy are not a monolithic population. They represent a dazzling spectrum of ages, chemical compositions, and evolutionary stages. Studying these stellar populations and their metallicity gradients, how the abundance of heavier elements changes across the galaxy, is like reading the galaxy's autobiography, revealing its intricate history of star formation, gas enrichment, and mergers. What dramatic tales do these diverse stellar families tell us about M31's past, and what riddles do their distributions continue to pose? Stars are primarily composed of hydrogen and helium, the elements forged in the Big Bang. All heavier elements, what astronomers refer to as metals, are created in the fiery crucibles of stellar interiors through nuclear fusion, and then dispersed into the interstellar medium by stellar winds or spectacular supernova explosions. Subsequent generations of stars then form from this enriched gas, inheriting a higher metallicity. Therefore, older stellar populations tend to be metal-poor, while younger stars are more metal-rich. By measuring the metallicities of stars in different regions of M31, astronomers can reconstruct its star formation history and the processes of chemical enrichment across its vast expanse. Observations, particularly from the Hubble Space Telescope and ground-based spectroscopic surveys, have revealed fascinating metallicity gradients in M31. Generally, the inner regions of M31, particularly its central bulge, are found to be very metal-rich, indicating a rapid and intense period of early star formation that quickly enriched the gas with heavy elements. As one moves outwards into the disk and then into the halo, the metallicity generally decreases. This is a common pattern in large spiral galaxies, reflecting the inside-out formation of galactic disks and the accretion of metal-poor dwarf galaxies into the halo.
However, the precise details of these gradients in M31 hold some unresolved riddles. Are the gradients smooth, or are there abrupt changes or reversals that might indicate past merger events or significant gas inflows? For instance, some studies of M31's disk have suggested a flatter metallicity gradient than expected in some regions, which could be explained by radial mixing of stars and gas or by the influence of its central bar. The presence of distinct stellar populations with varying metallicities within the tidal streams of the halo also provides crucial evidence of accreted dwarf galaxies, each contributing its own unique chemical signature.
The drama of this research lies in its ability to piece together M31's violent past. By comparing the metallicity of stars in its main body to those in its halo streams, astronomers can distinguish between stars that formed in situ within M31 and those that were brought in by mergers. For example, some globular clusters in M31's halo are extremely metal poor, suggesting they are very ancient and formed in the galaxy's earliest phases, or were accreted from very primordial dwarf galaxies. Others have higher metallicities, indicating they might have formed later or were absorbed from more evolved satellite galaxies. The ongoing quest to precisely map the stellar populations and metallicity gradients within M31 is a complex archaeological endeavor. It requires not only precise photometric measurements to determine stellar ages, but also high-resolution spectroscopy to measure chemical compositions. Each new data point, each resolved star, contributes to a richer, more detailed narrative of the Andromeda Galaxy's dramatic birth, turbulent growth, and complex evolution, offering invaluable insights into the chemical evolution of galaxies across the universe.
The majestic Andromeda Galaxy, far from being a pristine, isolated entity, is a product of billions of years of cosmic cannibalism. Its immense size and structure have been sculpted not just by internal dynamics, but by countless accretion events and minor mergers, where smaller dwarf galaxies have been gravitationally pulled in, torn apart, and absorbed into the larger galactic whole. Understanding the precise role of these ongoing and past mergers in M31's growth is a dramatic, complex riddle that holds crucial clues to its evolution and its ultimate destiny. The evidence for these accretion events is strikingly visible in M31's vast stellar halo. Observations have revealed intricate tidal streams, long, wispy trails of stars that are the ghostly remnants of dwarf galaxies being ripped apart by Andromeda's powerful gravity. These streams are like cosmic breadcrumbs, tracing the paths of devoured systems. One of the most prominent examples is the giant Southern Stream, a vast structure of stars extending for tens of thousands of light years, believed to be the debris of a dwarf galaxy that was accreted by M31 perhaps a billion years ago. The discovery and mapping of these streams, often requiring painstaking observations of faint, diffuse light, are triumphs of modern astronomical detective work. By studying the kinematics, or motions, and stellar populations, ages and metallicities, of the stars within these streams, astronomers can reconstruct the properties of the original dwarf galaxies and the timeline of their accretion. This provides a direct observational test of the hierarchical galaxy formation model, which posits that large galaxies grow by progressively accreting and merging with smaller ones. M31 provides a unique nearby laboratory for observing this process in action, offering a much more detailed view than can be obtained from distant merging galaxies. However, many riddles persist. How many dwarf galaxies has M31 truly absorbed over its lifetime? Are there more, even fainter tidal streams yet to be discovered, perhaps hidden by foreground stars or too diffuse for current telescopes? What was the original size, gas content, and dark matter distribution of these accreted systems? The precise impact of these minor mergers on M31's evolution is also debated. Did they trigger bursts of star formation, inject new gas, or simply add to the stellar halo? Some theories suggest that accretion events can also trigger the formation of spiral arms or contribute to the growth of the central bar.
The drama of accretion is ongoing. M31 continues to interact gravitationally with its known satellite galaxies, such as M32 and NGC 205. These satellites are themselves likely being gradually stripped of their outer stars by M31's tidal forces, slowly contributing to its growing halo. The interaction with the relatively massive Triangulum galaxy, M33, which is also part of the local group, is another important factor, though its precise orbit and interaction history with M31 are still subjects of active research. Ultimately, M31's growth through accretion and minor mergers is a dynamic process that has shaped its present structure and will continue to influence its future. Understanding these past cosmic collisions is not just about M31. It's about unraveling the fundamental processes by which galaxies across the universe have assembled and evolved, offering profound insights into the violent yet ultimately constructive nature of cosmic evolution.
One of the most powerful and intriguing tools available to astronomers for understanding the mass distribution, particularly the elusive dark matter content of galaxies like M31, is gravitational lensing. This phenomenon, a direct consequence of Einstein's theory of general relativity, occurs when the gravity of a massive object, like M31, bends and distorts the light from more distant background sources. By carefully observing these distortions, astronomers can effectively weigh the foreground galaxy, revealing not just its visible mass, but also the invisible influence of its dark matter halo. What profound insights does this cosmic magnifying glass offer into the riddles of M31, and what challenges does it present? Imagine a vast cosmic lens. That's what M31's immense gravitational field acts as. When light from a very distant galaxy or quasar travels towards us and happens to pass close to M31, its path is bent. If the alignment is just right, the background source can appear magnified, distorted into arcs, or even create multiple images. This is known as strong gravitational lensing. While strong lensing is more commonly observed with massive galaxy clusters acting as lenses, the Andromeda galaxy, with its immense mass, can also produce more subtle lensing effects on background galaxies. A more common application for galaxies like M31 is weak gravitational lensing. In this scenario, the distortions are much more subtle and cannot be seen by eye in individual images. Instead, astronomers look for tiny, systematic alignments or stretches in the shapes of many background galaxies that are subtly lensed by M31's gravitational field. By statistically analyzing the shapes of hundreds or thousands of distant galaxies viewed through and around M31, astronomers can create a map of the gravitational potential and thus the total mass distribution of the Andromeda galaxy. This technique is particularly valuable because it directly probes the total mass, including dark matter, without relying on assumptions about the motions of stars or gas.
The drama of using gravitational lensing for M31 lies in its incredible technical difficulty. The galaxy is relatively close, meaning that background sources are often too faint or too obscured by M31's own stars and dust. Furthermore, the lensing signal is extremely weak, requiring highly sensitive telescopes and sophisticated image processing techniques to detect. Despite these challenges, astronomers have begun to apply weak lensing techniques to M31, providing independent estimates of its total mass and the extent of its dark matter halo. These measurements are crucial for cross-validating estimates derived from stellar kinematics and virial mass calculations. For example, a study in 2018 using data from the Pan-Andromeda Archaeological Survey, PANDAS, combined with gravitational lensing techniques, provided new constraints on M31's mass, suggesting it might indeed be more massive than the Milky Way. However,
The precise extent and shape of the dark matter halo derived from lensing still present riddles. Is the halo perfectly spherical, or is it slightly flattened or elongated due to past mergers or the influence of the central bar? Gravitational lensing, as a direct probe of mass, offers a powerful, independent way to address these fundamental questions.
Gravitational lensing is a cosmic X-ray vision, allowing us to see the invisible mass that dominates the Andromeda Galaxy. As observational capabilities improve, particularly with future telescopes capable of wider field, high-resolution imaging, gravitational lensing promises to become an even more powerful tool for unraveling the deepest riddles of M31's dark matter architecture and its gravitational influence on the surrounding cosmos. At the heart of the Andromeda Galaxy lies a supermassive black hole. Yet unlike many active galactic nuclei, AGN, in distant galaxies that blaze with incredible luminosity, M31's central behemoth, known as P2, is remarkably quiescent. It's largely in a state of slumber, consuming very little gas and emitting only faint levels of radiation. This relative inactivity presents another intriguing riddle. Why is M31's central supermassive black hole so quiet, especially given its estimated mass of around 10 to the 8th solar masses? And what does this quiescence tell us about the history and future of this cosmic titan? Many supermassive black holes at the centers of galaxies are voracious eaters, actively accreting gas and dust from their surroundings. As this matter spirals inwards, it forms an intensely hot accretion disk, generating powerful jets and outflows that can extend for thousands of light years, emitting vast amounts of X-rays, radio waves, and gamma rays. These active galactic nuclei are some of the most luminous objects in the universe. M31's P2, however, exhibits only very low levels of X-ray and radio emission, consistent with a very low accretion rate. It's like a sleeping giant, quietly waiting. The drama of this quiescence lies in its implications for galactic evolution. The activity of a central black hole is intimately linked to the growth and evolution of its host galaxy. Powerful AGN outflows can heat and expel gas from the galaxy, potentially suppressing star formation. Conversely, bursts of star formation can feed the black hole. The quiescent nature of P2 suggests that M31 is currently not undergoing a major episode of gas infall to its core. This contrasts with the Milky Way's supermassive black hole, Sagittarius A star, which is also largely quiescent, but occasionally shows flares, indicating minor accretion events.
So why the slumber? One explanation is simply a lack of available fuel. The gas and dust in M31's inner regions might have been largely consumed by past star formation or expelled by previous periods of black hole activity. Without a fresh supply of gas, the black hole remains starved. Another possibility relates to the dynamics of the gas that is present. Even if there's gas, it might not be efficiently flowing down to the black hole due to turbulent motions, strong magnetic fields, or the influence of the dense nuclear star cluster. The double nucleus structure, which we discussed earlier as an eccentric disk of stars, might also play a role, perhaps stabilizing gas at larger radii rather than allowing it to plunge into the black hole. Astronomers use observations from X-ray telescopes like Chandra and XMM Newton and radio telescopes like the Very Large Array to probe the faint emissions from M31's nucleus. These observations help to constrain the accretion rate and the physical processes occurring very close to the event horizon. While its quietude makes it harder to study directly, it paradoxically offers unique insights into the long periods of galactic evolution when central black holes are not actively feeding. The quiet nature of M31's supermassive black hole is a profound riddle, hinting at the complex interplay between a galaxy's central engine and its overall evolution.
Its slumber today might be a prelude to future activity, especially during the impending merger with the Milky Way. When the two galactic cores finally merge, the increased gas infall triggered by the chaotic gravitational interactions could awaken both black holes, leading to a truly dramatic luminous phase for the newly formed Andromeda galaxy.
The grand cosmic drama of the Andromeda Galaxy culminates in an event that will reshape our galactic destiny, the collision and eventual merger with the Milky Way, forming a colossal new galaxy often dubbed Andromeda. This is not just an intriguing scientific prediction, it's a dramatic vision of our far future, forcing us to contemplate the ultimate fate of our cosmic home and the profound implications for the universe itself. What will this merged galaxy look like, and what long-term consequences might this titanic embrace have for the local group and beyond? Approximately 4.5 billion years from now, the initial gravitational dance will begin. The two galaxies, already feeling each other's pull, will start to distort, their stellar arms stretching and unraveling. This first pass will be a dramatic event, as stellar streams are flung out into intergalactic space, and bursts of star formation might be triggered by the compression of gas clouds. However, this won't be a catastrophic smash-up of stars. As we've discussed, the vast emptiness of galaxies makes direct stellar collisions exceedingly rare. Instead, it will be a gravitational ballet, pulling and pushing matter on a galactic scale. Over the next few billion years, M31 and the Milky Way will undergo several close encounters, each time losing kinetic energy due to dynamical friction, primarily with their massive dark matter halos. With each pass, they will draw closer, their disks becoming increasingly distorted and their structures eventually dissolving. The familiar spiral arms will vanish, replaced by chaotic streams and clumps of stars. Finally, after several passes, they will coalesce into a single, much larger, more spheroidal galaxy. This new entity, Andromeda, is expected to be an elliptical or lenticular galaxy, a testament to the transformative power of galactic mergers.
The new Andromeda will be a scene of profound change. The supermassive black holes at the centers of M31 and the Milky Way, having already been spiraling towards each other for eons, will eventually merge. This final collision of cosmic leviathans will be an incredibly energetic event, generating powerful gravitational waves that will ripple through space-time. While the process itself will be hidden behind event horizons, the surrounding accretion disks might flare dramatically as vast amounts of gas are funneled into the newly formed, even more massive, supermassive black hole. What are the long-term implications of Andromeda? For the local group, it means the eventual consolidation of its two largest members. Smaller dwarf galaxies currently orbiting M31 and the Milky Way will either be absorbed into Andromeda or flung out into the expanding universe. The local group will become a more compact, singular entity, dominated by this new galactic behemoth. Beyond the local group, the merger will contribute to the ongoing process of cosmic evolution, where smaller structures merge to form larger ones, ultimately shaping the large-scale structure of the universe. The philosophical implications are profound. If humanity, or its descendants, still exists in 4.5 billion years, their night sky will be utterly transformed, a dramatic and beautiful testament to cosmic impermanence. The realization that our galactic home is not eternal, but part of a grander, ever-changing cosmic narrative, pushes us to reflect on our place in this vast, dynamic universe. The future of Andromeda is a reminder that the universe is alive, constantly evolving, and full of astonishing, dramatic transformations.
Beyond the visible stars and dark matter halos, the Andromeda Galaxy is inextricably linked to the intergalactic medium, or IGM, the vast, diffuse expanse of gas and plasma that fills the space between galaxies. Understanding the interaction between M31 and this cosmic reservoir,
Particularly the flow of gas into and out of the galaxy is a crucial yet challenging riddle. These gas flows are the cosmic fuel that drives star formation, regulates galactic growth, and provides profound insights into the exchange of matter and energy within the local group and beyond. What dramatic secrets do these invisible cosmic currents hold about M31's past, present, and future? Galaxies like Andromeda are not isolated systems. They are constantly interacting with their surrounding environment. Gas from the IGM can fall into the galaxy, providing fresh fuel for star formation. Conversely, powerful outflows from supernova explosions and active galactic nuclei can eject gas back into the IGM, enriching it with heavy elements forged within stars. This continuous cycle of infall and outflow is known as the galactic baryon cycle, and it's a fundamental process that shapes galactic evolution. For M31, observing and quantifying these gas flows is incredibly difficult, as the gas is often extremely diffuse and emits very faintly.
Beyond the visible stars and dark matter halos, the Andromeda Galaxy is inextricably linked to the intergalactic medium. One of the key riddles is understanding the rate at which M31 accretes new gas from the IGM. Theoretical models suggest that galaxies need a continuous supply of fresh gas to sustain star formation over billions of years. Evidence for this accretion comes from observations of high-velocity clouds of neutral hydrogen, which appear to be falling into the galaxy. These clouds are often detected using radio telescopes, which can map the distribution and kinematics of neutral hydrogen. The drama of this detection lies in identifying these faint, distant gas clouds amidst the much brighter emission from the galactic disk, requiring exquisite sensitivity and sophisticated data analysis.
Furthermore, the outflow of gas from M31 is also a critical component. Powerful supernova explosions can drive galactic winds, pushing gas and heavy elements out of the disk and into the halo or even the broader IGM. This feedback mechanism is crucial for regulating star formation and preventing galaxies from growing too large too quickly. By studying the distribution of hot X-ray emitting gas in M31's halo, observed by X-ray telescopes like Chandra and XMM Newton, astronomers can infer the presence of these outflows. The challenge lies in distinguishing gas that has been ejected from M31 from the primordial gas of the IGM, or gas stripped from infalling dwarf galaxies. The interplay between M31 and the intergalactic medium is also critical for understanding the evolution of the local group. The gas within the local group is not static. It is influenced by the gravitational potentials of both M31 and the Milky Way. As these two galaxies approach each other, the gas between them will be compressed and heated, potentially leading to new phenomena. The precise amount of gas in the IGM around M31, its temperature, density, and metallicity are all crucial parameters that remain largely unknown and pose significant observational challenges. The cosmic fuel of the intergalactic medium and its dynamic interaction with M31 represent a dramatic, invisible frontier of astronomical research. Unraveling these gas flows is essential not only for understanding M31's growth and star formation history, but also for comprehending the broader processes that shape galaxies and the distribution of matter throughout the universe.
The Andromeda Galaxy is not alone. It is accompanied by a retinue of dozens of smaller satellite galaxies, gravitationally bound to its immense halo. These dwarf galaxies, from the relatively bright and prominent M32 and NGC 205 to countless fainter, more diffuse systems, are not merely passive companions. They are active participants in M31's gravitational domain. Their dynamics and properties hold crucial clues to Andromeda's total mass, dark matter distribution, and accretion history. What dramatic insights do these celestial dependents offer into the riddles of their cosmic overlord? M31 and NGC 205 are the most notable of Andromeda's satellites.
M32 is a compact elliptical galaxy, remarkable for its high surface brightness and dense stellar core. NGC 205, also an elliptical, is more diffuse and exhibits some signs of recent star formation in its inner regions. Both galaxies are strongly influenced by M31's powerful gravity. Studies of their stellar populations and kinematics can reveal the extent of M31's gravitational pull and provide indirect evidence for its dark matter halo. For example, the disruption of M32 by M31's tidal forces might have played a role in its compact structure, though the exact extent of this interaction is still debated. Beyond these two prominent companions, M31 is surrounded by a swarm of fainter, much more diffuse dwarf spheroidal galaxies. These are some of the most dark matter-dominated objects in the universe, making them prime targets for understanding the nature of dark matter. Detecting these ultra-faint dwarfs is an immense observational challenge, often requiring deep, wide-field surveys with telescopes like the Canada-France-Hawaii Telescope, CFHT, and the Pan-Andromeda Archaeological Survey, PANDAS. The drama of this discovery lies in finding these incredibly dim, extended objects amidst the overwhelming glare of M31's brighter stars.
The distribution and motions of these satellite galaxies around M31 present several unresolved riddles. Do they orbit in a preferred plane, forming a plane of satellites, similar to what has been observed around the Milky Way? The existence of such planes challenges some standard cosmological models, which predict a more random distribution of satellite orbits. If M31 also exhibits such a planar structure, it could suggest a common formation mechanism for these satellites, perhaps related to past major mergers, or even indicate a challenge to current dark matter models. Furthermore, studying the stellar content of these satellites can reveal their individual star formation histories and their chemical compositions. Have they all had similar evolutionary paths, or have some experienced unique bursts of star formation or quenching due to their interactions with M31? The discovery of new, extremely metal-poor stars in some of M31's dwarf spheroidals suggests they are truly ancient relics from the early universe, preserving clues about the very first generations of stars. The retinue of Andromeda's satellite galaxies is a dynamic, complex system, continually being shaped by its host galaxy. Each satellite is a small puzzle piece in the larger cosmic riddle of M31. By unraveling the mysteries of these celestial companions, astronomers gain profound insights into the dominant gravitational influence of Andromeda, the distribution of its dark matter, and the intricate processes of hierarchical galaxy formation across the universe.
The Andromeda Galaxy's present grandeur is not solely a product of its initial formation. It's a living testament to a turbulent past, etched with the scars and triumphs of numerous past collisions and merger events. The faint, ghostly echoes of these cosmic encounters are preserved in M31's stellar halo, forming intricate tidal streams and stellar shells. Unraveling the stories of these ancient collisions is a dramatic archaeological endeavor, providing crucial insights into how this cosmic titan grew and evolved over billions of years. As we've touched upon, the tidal streams in M31's halo are the most direct evidence of its cosmic cannibalism. These long, slender trails of stars are the remnants of smaller dwarf galaxies that were gravitationally torn apart as they orbited too close to M31's immense mass. Imagine a delicate pearl necklace being stretched and broken by an unseen hand. That's what happens to these unfortunate dwarf galaxies. The most prominent of these is the giant Southern Stream, a vast, diffuse structure discovered through painstaking
On the 24th of April, 1990,
believed to
the
be the
NASA
debris of
ESA
a
Hubble
dwarf
Space
galaxy
Telescope
that M31
was sent into
devoured
orbit
perhaps a
above the
billion
Space
years
Shuttle
ago.
Discovery, the
The drama
first space
of studying
telescope
these
of its
streams
kind.
lies in their ethereal nature. They are
It offered
incredibly
a new
diffuse
view
and
of the
faint,
universe
often
and has, for
requiring
30
specialized
years,
observational
surpassed
techniques
all
and
expectations,
wide-field
beaming
imaging
back
surveys
data
to
and
detect.
images that have
Once
changed
identified,
scientists'
astronomers
understanding
then
of the
analyze
universe
the
and the
kinematics and
public's
stellar
perception of
populations of
it.
the stars within these streams. By
Hubble's
measuring their
discoveries
velocities
have
and chemical
revolutionized nearly all
compositions, they can
areas of current
reconstruct the
astronomical
original orbits
research,
of the devoured
from
galaxy
planetary science
and
to
estimate
cosmology,
when these
and
merger
its
events
pictures
occurred.
are
This
unmistakably
process
out of
allows
this world.
astronomers to literally
This
rewind
video will
cosmic
reveal
time,
some of Hubble's
tracing
biggest
the
science
violent, yet
discoveries
formative
throughout
history
its
of
3
Andromeda.
decades of
But the
operation.
riddles don't end there. How many distinct merger events have contributed to M31's halo? Are there more, even fainter streams that remain undiscovered, perhaps hidden by the glare of brighter stars or
An
blended
early
with
and
other
memorable
features?
result is the Hubble
Some
Deep
theories
Fields.
suggest that M31 might have undergone a more significant
These are extended
major
observations
merger
of a
event in its
particular
distant
region of the
past,
sky
perhaps with a
intended to
galaxy
reveal faint
comparable in
objects.
size to the
By
Triangulum
collecting the
galaxy.
light from them for an
Such an event
appropriately long
could explain
time.
the formation of its prominent central bulge, and perhaps even trigger the formation of its bar and spiral arms.
These images
However,
fascinated
conclusive
scientists
evidence
and the
for
general
such a
public
dramatic
alike
early
as the
merger is
thousands
still
of
being
galaxies
sought.
captured in
The
single
presence
images
of a diffuse,
spawned widespread
extended
fascination
stellar halo,
and amazement.
much like that observed in our own Milky Way, is a common feature of large
The
galaxies
original and
and
now
is strong
famous Hubble
evidence
Deep
for
Field
hierarchical
image,
galaxy
released in
formation.
1996,
M31,
consisted of an
being
area of
our
sky
closest
with a
major
width
galactic
equal to
neighbor,
just 1/12
offers
that
an
of the full moon.
unparalleled opportunity
In
to
it,
study
Hubble
these
found
processes
almost
in detail.
3,000 distant
Each
galaxies.
newly discovered stream, each analysis of its
The
stellar
Hubble
content
Ultra Deep Field
adds
from
another piece to the
2004
complex
was the
puzzle of
deepest
Andromeda's
portrait
growth.
of the visible universe
These
ever
past
achieved
collisions
by
are not just
humankind.
historical footnotes. They are fundamental
The
processes that have
2012
shaped
Hubble
the very
Extreme Deep
structure
Field
and
was an
evolution of this
impressive
cosmic
combination of
titan,
many existing
setting the stage
exposures,
for its
over
dramatic
2,000
future
of them,
encounter
into
with our
one
own
image.
galaxy.
While we've discussed star formation in specific regions,
The
a
results were
persistent,
astonishing for
overarching riddle
astronomers.
for the
By
Andromeda
studying
galaxy
the
is
thousands
its
of galaxies
global
captured
star
in these
formation
deep
rate,
field
or
observations,
SFR.
including some of the
Despite
most
being
distant
larger and
primeval
more
galaxies,
massive in terms
they
of
were
stellar
learning
mass
more about
than
the
the Milky
very
Way,
early universe.
M31 appears to be
The
forming
bulk of
stars
the
at a
early and remote
significantly lower
galaxies
rate
had not
overall.
yet had time to form
This
stars,
surprising
and
quiescence,
were also
compared to our own
characterized
galaxy,
by an
poses
atypical
a
shape,
profound
as
challenge
they seem
to
to
our
be
understanding
smaller
of
and more
galactic
irregular
evolution.
than those
Why
nearer
is
to
this
us.
cosmic giant so
This was
relatively
taken
quiet
as a
in its
clear
stellar
indication
nurseries?
that
And what does
galaxies
this
form
tell
by
us about the
merging together
long-term fate
smaller
of large
objects.
spiral galaxies? The Milky Way's average star
The
formation
Hubble
rate
Frontier
is
Fields
estimated
Observing
to be
Campaign
about 1 to 2
drew
solar
upon the
masses
power
per
of
year,
massive clusters of
meaning that
galaxies
roughly 1
to
to 2
unleash the
times the
full
mass of our
potential
Sun
of the
is
Hubble
converted
Space
into
Telescope.
new stars annually. For M31, estimates generally place its global star formation rate
Hubble's
at a lower
sensitivity
value,
and high resolution
perhaps around
allow it to see
0.4 to
faint and distant
0.7
gravitational
solar masses
lenses
per year.
that are harder to
This is a
detect with
perplexing
ground-based
observation.
telescopes.
A larger galaxy
Gravitational
with more
lensing
gas
is a
and deeper
phenomenon created
gravitational
by
well
extremely
might
concentrated
intuitively
masses,
be expected to be more
like the
efficient
cores
at
of
forming
galaxies
stars,
of galaxy
or at least
clusters.
comparable. Why
Their
the
strong
discrepancy?
gravity warps the surrounding
Several factors
space,
could
and
contribute
light from
to
distant
M31's
objects
lower
traveling
global
through that
SFR.
warped space is
One
curved
leading
away from its
hypothesis
straight-line
involves its
path,
gas
as if
content.
passing through a lens.
While M31 is massive, it appears to have a relatively
Hubble
lower
can
fraction
resolve
of
details
cold
within the
molecular
multiple
gas
banana-shaped
compared to
arcs
the Milky Way,
that are one of the
especially
main
in its
results
inner
of
regions.
gravitational lensing,
Cold molecular
as
gas
the
is
images
the
of
raw
background
material for
sources
star
are
formation.
distorted.
If the supply of this fuel is depleted or less abundant, then star
An
formation
important
will
consequence
naturally
of
slow
lensing
down.
distortion is
Why
magnification,
might M31 have less
allowing
cold
us
gas?
to observe objects
It could be
that
due
would
to
otherwise
past
be too
merger
far
events
away
that
and
heated
too
or
faint to
expelled
be
gas,
seen.
or perhaps a more efficient conversion of gas
Hubble
into
makes
stars
use
in
of
its
this
early
magnification
history,
effect
leaving
to
less for
study
current
beyond
star
the
formation.
sensitivity
Another
of its
factor could be
2.4
stellar
meter
feedback.
diameter primary
If
mirror.
M31 experienced
By showing
more
us the
intense
most
bursts
distant
of star
galaxies
formation
humanity
or more
has ever
powerful
encountered.
supernova explosions in its past, these events could have heated the
Hubble's
interstellar
observations
medium
of lensing
and driven
effects
out large
have also
quantities
given
of
us a
gas,
glimpse depths of the
preventing
cosmos
it from
that will be
collapsing to form
unveiled
new
by
stars.
the upcoming NASA
Similarly,
ESA
if
CSA
its central
James Webb Space
supermassive black
Telescope.
hole had more active phases in the past, its powerful outflows could
could have effectively sterilized the inner
One of
regions
Hubble's
the galaxy,
initial core
inhibiting
purposes
star
was
formation.
to determine the rate of
The
expansion of the
quiescence of
universe,
M31's
known
current
to
central
astronomers
black hole
as the
supports
Hubble
this
constant.
idea, suggesting a
This
period
value
of past
is an essential
activity might
ingredient
have cleared
needed
out
to
its
determine the
immediate
age,
surroundings.
size, and fate
The
of the
structure
cosmos.
of M31's bar and spiral arms also plays a role.
Before Hubble was
While
launched,
bars can
the
funnel
value of
gas
the Hubble
inwards,
constant
they can
was
also
not known
stabilize
precisely,
gas at certain
and
radii,
calculations of the
preventing it
universe's
from
age
collapsing.
ranged from
The
10
exact
billion to
efficiency
20
of gas
billion
funneling
years.
and compression
Now,
within
astronomers
M31's
using the Hubble
specific
Space
spiral
Telescope's
pattern
data and
might be less
observations
conducive
have
to
refined their
widespread star
estimates of the
formation
universe's
compared
present
to the Milky
expansion
Way.
rate and
The
are
10
working to make it more
kiloparsec ring
accurate.
of star formation
Hubble's
is a notable
refined
exception,
distance values have
suggesting
helped to put
localized
the age of the
conditions are
universe
still
at
favorable there.
13.8
The
billion
puzzle
years.
of M31's low global star formation rate
While
is a
improving the
dramatic
measurements of the
challenge to
Hubble
our models
constant,
of galaxy
the
evolution.
Hubble Space
It
Telescope's
suggests
data
that
have
even
also
for
supported
seemingly
the
similar
development and
spiral
use of the
galaxies,
cosmic
the
distance
internal
ladder,
dynamics,
which is an
merger
important
history,
scientific tool
and gas
that is
reservoirs
used to measure
can lead to
accurate
vastly
distances
different
to galaxies
evolutionary
near
paths.
to and far from
By
Earth.
unraveling this mystery, astronomers gain deeper
To do
insights
this,
into the
astronomers
complex
use
interplay
Hubble
of
to
forces
measure the
that govern the
distances to a
birth
class
and
of
death of
pulsating
stars on
stars
galactic
called
scales,
Cepheid variables,
ultimately
which are
informing our
used as
understanding of
milepost
the universe's
markers.
long-term stellar demographics.
The
Once the
Andromeda
Cepheids
galaxy
are
isn't just a
calibrated,
fascinating
astronomers
object of
move
study in
beyond
its
our
own
Milky
right.
Way
It
to
serves as
nearby
a critical
galaxies
cosmic
for other
laboratory for
reliable
testing and
yardsticks.
refining fundamental cosmological models,
Supernovae,
particularly
exploding
those describing
stars
the
that
formation
flare
and
with
evolution
the same
of
amount of
structures in the
brightness.
universe. Its proximity,
Astronomers use
its
the
clear
Cepheids
interaction with
to
the Milky Way,
calibrate the
and its
relationship
wealth of
between
observable
absolute
features
luminosity
make it an
and
invaluable
apparent brightness
testbed
relation for
theories ranging from
supernovae,
dark matter
which
and
is a
dark
function
energy
of the
to
distance from
hierarchical
us of their
galaxy
host
formation.
galaxy.
What dramatic
We
insights
detect
does M31
supernovae
offer
in
into the
galaxies
very
hundreds of
fabric of our
millions of
cosmos?
light years from us,
And what profound
giving us a
challenges does
powerful
it pose
tool
to our
for
reigning
calibrating
cosmological
redshifts
paradigms?
at larger distances
One of the
than
most
Cepheids
significant
can.
contributions of M31
However,
is its role in
scientists
validating the
discovered
lambda
that
CDM,
supernovae at
or
higher
LCDM
redshifts
model, the
were
standard
fainter
model of
than one would
cosmology.
expect when assuming a
LCDM
constant
posits
expansion
that
of
the
the
universe
universe,
is dominated
meaning
by dark
they were
energy,
further away.
with cold dark matter
These
making up only a
observations
small
helped
fraction.
astronomers to then
This
determine
model
how
successfully
fast the
predicts the
universe
large-scale
is
structure of the
expanding
universe,
over time.
the cosmic web of galaxies,
To their
clusters, and
surprise,
voids.
the data implied
However,
that the universe
testing
has not
LCDM
been
on
expanding
galactic
at a
scale,
constant rate,
particularly
but
with
instead
individual
is
galaxies, has
accelerating.
presented some challenges.
Many scientists
M31,
believe this
with its
acceleration
well-studied
is
dark
caused by
matter
something
halo
called
and its
dark
clear
energy
history of
that must
accretion,
make up about
provides an
70%
unparalleled
of the entire
opportunity to
universe.
test LCDM's predictions
By
for galaxy
observing how
formation.
dark energy behaves
For
over
instance,
time,
the number and
astronomers hope to
distribution of
gain
its
a better
satellite
understanding
galaxies
of what
are
it
compared
is
to
and
predictions
how it
from
might
LCDM
affect the
simulations.
future of the cosmos.
Some early comparisons
The
revealed
telescope
a missing
also carried out
satellites problem,
surveys
where
and
simulations
developed
predicted
new
more
methods
dwarf
to look
galaxies
for
than
clues
observed
about
around
the
large
equally
galaxies.
mysterious dark matter.
However, more refined
Which makes up
simulations,
about
which include the
27%
effects
of
of
the
stellar
universe.
feedback and environmental stripping, have largely resolved this discrepancy, bringing
Astronomers
observations
used
of
Hubble to
M31
create a map
satellites
of
into
everyday
closer
visible
alignment with
matter,
LCDM
from which
predictions.
they could trace the
impending
large-scale
collision between
distribution of
M31
dark
and the
matter
Milky Way
by
is another
studying
critical
how
test.
its gravitational
The precise
presence
trajectory
distorted
and
light in
future
the
merger
images.
outcome depends sensitively on the distribution of dark matter in both galaxies,
Hubble has
as
also
predicted by
lifted the
lambda
veil
CDM.
surrounding the cosmic
If the
monsters
observed
that
motions
lurk
of
at the center
M31
of
in the
most
Milky Way,
galaxies,
or the characteristics of the
supermassive
resulting
black holes.
Andromeda galaxy were to drastically
Using its
contradict the
spectroscopic
simulations,
observing
it would force a
capabilities,
re-evaluation
Hubble peered
of
into the
fundamental
galaxy
aspects
cores
of the
and
lambda
found that the
CDM model
stars there
or
moved
our
in tight
understanding of dark
orbits
matter.
at enormous
The drama
velocities.
of this future event
This
is
strange
that it
behavior
serves as a massive
indicated the
real-world
presence of a
experiment
truly
for our
colossal
cosmological
gravitational
theories.
field that could only
Furthermore,
be produced by a
M31's role
supermassive
in the
black hole.
dynamics of the local group
Hubble
provides
provided
crucial
the
insights
first
into the
solid
interplay
proof
of
of their
gravity and the
existence.
expansion of the universe.
Today,
The
it is
local
known that
group
there is
is
a
a
black hole in the
gravitationally
center
bound
of
system,
almost every
meaning that
galaxy.
within its boundaries, the gravitational pull between
between galaxies
Another
overwhelms
phenomenon
the
that
expansion of
Hubble's
space
instruments have
caused by dark
observed
energy.
throughout the years
This makes
is
it
quasars.
an ideal environment
to
These
study
are
the precise
powerful jets of
gravitational
energy that
interactions
come from
between
extremely
galaxies
luminous
without the
galactic
confounding
centers.
effects of cosmic expansion.
The power from a
M31,
quasar
as
is
the dominant
enormous, and
gravitational
they
anchor of the
typically
group,
have
dictates
luminosities
much of its
thousands of
dynamics.
times brighter
The
than the Milky
ongoing
Way.
riddles of M31, its
In
exact
1996,
mass, its dark matter
Hubble's
distribution,
100,000th
its star
exposure
formation history,
was a quasar
and its
located
accretion of
9
smaller
billion
galaxies
light-years from
all
Earth.
serve as critical inputs and tests
More recently,
for cosmological
Hubble discovered
models.
the brightest
Each
quasar
new piece
ever
of data
seen
from
in the
Andromeda,
early universe.
each refined measurement either strengthens our confidence in our current
Hubble
understanding
has
of the cosmos
revolutionized
or
planetary
highlights
science
areas
in a
where our
number of
models need
ways
further
through
refinement.
its precise observations
M31
of
is
our
not
own
just a
solar
beautiful
system.
galaxy. It's a dynamic, living laboratory, constantly
Hubble has
challenging
charted
and
the
refining
dynamic
humanity's
activity on
most
Jupiter
ambitious
and its
theories
moon Io.
about the origin and evolution of the entire universe. Our cosmic voyage through the unsolved riddles
In
of the Andromeda
1994,
galaxy
it also
has been a
witnessed a
journey
comet
filled
crash
with both
into the planet's
adventure and
surface.
profound drama, showcasing a celestial neighbor that remains, for all its proximity, a tantalizing enigma. We've delved into the mysteries of its immense yet uncertain mass, which dictates the gravitational ballet it performs with our own Milky Way.
Hubble has
We've
also
explored
observed
the
the
perplexing
auroras on
patterns of its
several
star
of our solar
formation,
system's
revealing
planets,
a galaxy that keeps
including
its stellar
Saturn and
nurseries
Uranus.
surprisingly quiet in some regions while blazing with youthful
The
vigor in
telescope's
others.
data were also used to
pervasive,
study the origin
invisible
of the
embrace of
smallest
dark
known
matter
moon orbiting the
continues
planet
to shape its
Neptune,
architecture
known as
and dictate
Hippocamp.
its future, challenging us to weigh the unseen and the tantalizing possibility of exoplanets in its vast
In
expanse sparks
2013,
our deepest
Hubble provided the first
astrobiological
observational
curiosities.
evidence of water
From the
vapor
faint little
erupting
cloud
from the frigid
observed by
surface of
Alsufi
Jupiter's
over a
moon
millennium
Europa,
ago,
near
to the
its south
groundbreaking
pole.
Doppler shift measurements by Slipher that foretold its approach, and Hubble's breathtaking
The
resolution
telescope has
of over
also
100
captured
million
observations
stars.
of some
The
special
story of
interstellar visitors.
M31 is one of
In
relentless human
2018,
curiosity
Hubble
pushing the
studied
boundaries of
Oumuamua,
knowledge.
the first
The great
interstellar
debate
object
of
discovered
1920,
in the solar
with
system.
Andromeda at its heart, was a pivotal moment
In
that
cooperation
reshaped
with
our
other
understanding
ground-based
of the
telescopes,
universe,
it was
proving that our
determined that the
cosmos
object
is far
was likely
vaster
a comet
and more
and
intricate
was
than
moving
ever
away
imagined.
from the sun
Its
faster
spiral
than
arms
previously
dance to a
expected.
rhythm we are still deciphering.
In
Its past collisions
2019,
whisper
Hubble
tales of
provided
cosmic
astronomers
cannibalism,
with their
and its
sharpest and
quiescent
best
central
observation to
black
date
hole
of the
holds
interstellar
secrets of
visitor
galactic
comet
regulation. The
2I
mysteries of this
Borisov,
galactic giant
which
are
is
not
believed
merely
to have
academic
arrived here
puzzles.
from another
They're
planetary
fundamental
system
questions about
elsewhere
galaxy
in our
formation
galaxy.
and evolution, about the nature of dark matter, and ultimately about
Hubble's
our
high
place in a
resolving
universe
power
that is
has
far from
also been
static.
crucial in
The
the
impending
investigation
collision
of regions of
between
star
M31
formation,
and the Milky Way
both in the
is a
Milky Way
cosmic
and in
crescendo,
other galaxies.
a dramatic
And its
future event that
infrared
will redefine
capabilities
our galactic
have allowed
home
it to peer
and force
through
us
the
to
thick
contemplate
clouds
our
of dust and
cosmic
gas
destiny on
present in
scales
those regions.
unimaginable. This is our quest to decode M31's secrets, to unravel the cosmic riddles that could redefine our understanding of the universe's past and chart the course of its astonishing future.
The death of a star
The
can be
journey
as
to
beautiful
understand
and
the
interesting
Andromeda
as
galaxy
its birth.
is far from over.
Hubble
Each
has
new
observed
observation,
both sun-like
each
stars
scientific
as they
study
come to the end of their
peels back
lives in the
another
form
layer
of
of its
planetary
enigmatic
nebulae,
veil, revealing new complexities and inviting further
and
exploration.
massive stars
It
experiencing
reminds us
explosive
that the
deaths
cosmos
as
is a realm of
supernovae.
endless discovery, where every answered question often sparks a dozen more. We are, in essence, galactic
By studying them at
archaeologists,
different times in their
sifting through
lives,
cosmic
Hubble
dust
has
and
allowed
stellar
us to
light,
paint a more
piecing
complete
together the
picture of
grand
stars,
narrative of
the
creation.
building blocks of
The
galaxies.
Andromeda Galaxy stands as a magnificent testament to the
While not
universe's
one of its
enduring
original science
capacity for
goals,
wonder.
Hubble
A
has
constant
also made a name
invitation
for itself
humanity to
as an
look up,
exoplanet
to question,
explorer,
and to
in
continue its
particular by
never-ending
studying
adventure into the
exoplanet
unknown.
atmospheres.
If you've been
The
captivated by
chemical
this
makeup
journey
of
into
a
the heart
planet's
of galactic
atmosphere
mysteries
leaves
and
a
want to
unique
continue
fingerprint
exploring
on the
vast,
starlight that
unfolding
passes through
drama
it.
of the cosmos, be sure to subscribe to join us for more galactic adventures.